so that when you expose it, you can guarantee backward compatibility. You can make sure that in future you will be able to create a performant representation of the exposure you are going to make, right? Similarly, so that when the overall architecture of the GPU is becoming very complicated. It's not just the instruction. It is multiple memory layouts. It is communication with everything else around it. So we have to kind of build programming models, memory models, overall to make sure that all of the synchronization, etc., are working together, and that at the speed of 1 SE around, and things are being under the hood. Again, we saw a very large ecosystem of applications, and that means we will run on different architectures, OSs, etc. So for that, we need to have ABI which is efficient, and to get this maximum large, right? So running GPU is quite generalized, but it is still a specialized accelerator. So when you want to build large applications, you need to provide similar level of exposure as you do, so that you can build a large ecosystem of applications. And at the end of it, traditionally, CUDA has been often compiled, but there is more and more applications which are trying to go JIT mode, and that is just not the thing. It is necessity to get the performance and portability across the CUDA. We need to think through that. So while doing this, we also kind of innovate through different programming language design parameters. We need to look at memory consistency model. I just mentioned that there are 4 or 5 different levels of memories which are there. So when you want to write very large programs, you need to provide guarantees. You need to have provable guarantees for it. So we work on all the areas which are required for that as well, right? And I will kind of, the hardware software code design, I will kind of repeat it multiple times, because that problem needs to be solved at different levels and different things. So for example, at PTX level, you need to think about the hardware exposure, instruction exposure I mentioned. And you need to work with the architecture to say that how am I going to expose those things. Okay. So going one level below, down, right? So close to the hardware, right? So we have the basic engine of driving the performance of the architecture with the backend, right? So what does it do? So it is a unified backend. So it is not limited to CUDA or anything. We have a unified backend which not only handles the compute part, but it also handles paths from graphics side as well, and it tries to optimize it and generate code for all the different architectures. Really? So that itself kind of introduces complexity and challenges related to that. Obviously, we do all the classical optimizations, which everybody knows and loves, but at the same time, GPUs have its own challenges, right? So we, I think there is occupancy is one of the interesting challenges, which is easy to explain, right? So for example, we want to finish our work very fast, but at the same time, GPU has thousands of threads. So if you do not use those thousands of threads, then GPU is as good as the CPU, not running as maybe worse than the CPU, right? So we need to make sure we are utilizing all the threads, and most of the classical optimizations try to say that, okay, I want to target latency, right? So you do CAC, you do hoisting, everything kind of increases your register pressure, which in the end reduces the number of increases the number of registers and reduces the occupancy. Thereby, there is a complex trade-off which is to be had. Similarly, divergence is another interesting problem, right? So if you allow a normal program to run, then you will have conditions and you will start to branch. So if you do not have complex algorithms to minimize the divergence, then again you will not be able to use and maximize the performance of the GPU. Rapid architecture evolution, again, this is a common thread. We need to make sure newer and newer chips come in, newer architectures and features come in. I think for the backend, critically, because it's used across multiple features, like tomorrow, if many of you might be gamers, you hit the screen saying that compiling shaders, loading assets. This is all our responsibility, right? So we have to make sure that when you run a game, for example, thousands of shaders are compiled, and they need to be run in microseconds and milliseconds. And the complexity of those shaders itself is increasing, right? As the complexity of the games and visual fidelity of the game increases, similarly the shader also increases. So we have ourselves for that. Again, software hardware co-design, we work very closely with the architecture right from the start of when architecture design starts. We give feedback to them, okay, what works, what doesn't work. They have some ideas, we work with them to try them out in real compiler and see how the applications work, because architecture mostly work on macro benchmarks and they make sure things work for them, but that may not translate into real world performance in the GPU, right? So these are all interesting problems. So we kind of saw from top down on the GPU side. Let's try and switch focus on the CPU side, right? So again, CPUs are critical. So they are driving and making sure the GPUs are kind of fed consistently. They are orchestrating all the data going into the thing. The CPU is doing what it is good at. CPU is doing what it is good at, doing embedding lookups, scheduling, etc. So for that, I think we work in an open ecosystem on the CPU side. We support both the GCC as well as LLVM. All our development happens in open source. For that, GCC is the default compiler for all the platforms and data centers. So we need to make sure the applications are tuned for that. LLVM is up and coming. Many of the newer technologies are kind of getting developed on those. So CPU is in the large super GPU. CPU is equally important for the performance. Without that, everybody knows that Amdahl's law is going to kill you. Right? So, so what are the interesting things we do within the CPU land, right? So for example, obviously we work on the core optimizations, loop unrolling, PGO, etc. We also work on optimizing data scale and data center scale applications. So it is not sufficient. So most of our applications, for example, Grace, are working on very large programs, right? So they are not small programs. So we have to work on optimizations, for example, which look at and do, say, interprocedural analysis, do a PGO at much larger level to collect the data and tune it for this. So that makes sure that our customers who are running larger applications can get the optimizations for that. Again, we are also trying to involve ourselves, look at the whole stack problem, right? So it's not like only CPU focusing. We are trying to figure out how we can look at CPU and GPU together and optimize the interactions between them to get the performance for those, right? Again, software, hardware co-design. Again, on the last point is there are new and upcoming languages which are coming. So we have Flang, which is now forefront implementation on with a LLVM backend. We have Numba, which is Python with LLVM backend. So all our work which we do on LLVM, we try to feed it into those compilers so that the users of different languages can also benefit from the work we are doing on NVIDIA. Okay. So lastly, I think this is not talked a lot about. Mostly, whatever we have talked at different forums, we have mostly talked about the CPU and GPU. So today, I'll kind of give you an introduction of what happens on the networking side. So networking side, at a high level, what we have is it is a processor in an interface card. So in a NIC, we have a processor. It is based on RISC-V. It is open for programming. It is again, just like as we saw, it is rapidly evolving every year. So our idea is to provide a programmable high throughput solution for network computing, right? So that we have a very powerful and successful model in CUDA where we provide access to the GPU programming. Similarly, we want to provide access to the GPU packet processing to the network providers, right? So basically, The chip is essentially programmable GPUs, CPUs, along with hardware acceleration for those for networking, right? So we support it by specialized compiler stack and software stack, okay? And kind of, if we kind of dive deeper into the networking compiler, our goal is to maximize performance and throughput for those. We want to enable customers to develop packet processing pipelines of their own, right? So they may want to develop their own congestion protocols. They want to implement their different protocols depending on the overall network architecture. Because on the higher level CPUs and GPUs, there is more standardization, but there are multiple ways of the network configuration changes. So people may want to have different ways of handling it, right? So essentially, we have a Docker framework, which is kind of parallel to CUDA, where people can go and implement their own software. Okay. Okay. So moving on. So we kind of looked at overall work we do, but if you look at the challenges, they are very traditional and somewhat related to what work we do. So, but at the same time, kind of AI and this thing is knocking on our doors. And there are traditional problems on the current compiler design. Okay? So, if anybody from the industry has worked on a compiler for a very long time, the heuristics, everything, all the theory is perfect. Right? So we know exactly what is legal, what is illegal, what transforms we should do, what we should not do. Nothing breaks there. The things start breaking when you start putting in heuristics, right? So you can perfectly tune a heuristic for a single program, for a single architecture, and next day you get a new program, it's all gone. Okay, now I have a different program, different loop, my cache size is different, things change. We spend hundreds of hours trying to spend and try to tune them, right? So, okay, we have experts who go and, okay, I run this program, I run that program, I do this, I think this is the architecture doing, so I need to manage, put these special conditions here so that I can get and maximize the performance. They spend hundreds of hours trying to tune it, right? Other problem is we have very fixed pipelines, right? So there is no other way to have this. We have tried to solve this problem. Okay, I will do a optimize for size, optimize for time. I have O1, O2, O3, O4. There is no end to it. How do we solve this problem, right? Because if you just run the optimizations in different order, you will get maybe a better solution, right? People have tried to write programs which try to do phase ordering and do those things. But to the end, if you kind of take a step back and try to evaluate what is happening, all the experts which are doing is training themselves and trying to put that back into the compiler, right? Which is a perfect problem for AI, right? So that's what they are better at, right? So basically there are kind of different approaches here. So obviously there is a lot of research which has happened here. I will not be able to do justice to everyone who has worked on this. I just picked up a couple of examples to motivate people to try to look into this problem and see what more can be done. So one thing is heuristic tuning, right? So that is a very interesting problem to look at. So one thing we can do is we go use different techniques, look at data, try to train the heuristic, use RL, ML, whatever you like, and come up with a trained network, put it back into the compiler, do an online inference, and then make context-aware decisions, right? So, which is quite good. It basically avoids the brittle heuristic problem, right? It can adopt, it can look at the actual input which is coming in and can adopt to its heuristics to come up with a solution. We can automate the model tuning. If you have a new architecture which is coming in, you can retrain the network to solve the same problems. It has been proven useful in multiple applications already, like decisions related to function inlining, loop unrolling, register allocation, vectorization, all of them have utilized it to various degrees of success. So there are different ways of looking at it, right? So one way to say that, okay, I'm saving my time. The other way of looking at it is, okay, it is kind of tuning itself, right? So this is one thing. Something more ambitious is dynamic pipeline configuration. I don't think there is a good solution for it, but there are different approaches people have tried taking. So one is just combinatorial exploration, which can't be solved. So one is just group them together and cluster them and say that, okay, I'm going to cluster all my loop optimizations together. I will call an expert and say that, okay, how these should we do first this, first that, and then cluster them together, and then let some algorithm, RL algorithm or something to arrange it. So that is one way of doing it. Other is even more ambitious. Okay, I'll go run one pass, I'll look at the shader, I'll look at the output, I'll then choose a way, RL-based algorithm to figure out which one, which optimization to look at next, and then rinse and repeat. Obviously, it is very difficult, but if you take the trajectory of current AI models and other things, essentially we are getting more and more compute. So something which looks not feasible today might become more feasible. So more research and interest can go into this so that we can find optimal strategies to solve it. Okay. So it's basically pipeline. What can we do? So other thing which I wanted to look at, so this is where how AI can possibly infuse. The other way of looking at the problem is how the field of overall development itself is evolving, right? So every company here is trying to push you to go, okay, go use AI, get more productivity out of this, right? So different people are using different techniques to do accelerated development. They are hopefully doing enhanced debugging. Basically, you can tell it a bug and it can go and look at the code and tell you this is what is the problem and this tries to solve it. It can help you write unit tests as you go. So apparently things are improving. And then you can also get documentation. You can talk to the code, ask it what it is doing, etc. It's all nice, good. But if you look at it, this is in the end LLM, right? So it is guessing things. It is not going to give you the perfect answer, right? So it is going to create bugs into code, and people are not reading the code completely, right? So it is going to generate inefficient code. It is going to introduce security vulnerability. This is going to introduce hidden bugs in your problem, in your solution. So, okay, that is a problem. Again, I'm worried about the new generation, which hasn't coded, right? So they say, okay, I click this, I write a prompt, and it gives me an answer, right? So are people learning how to debug problems, how to read the code, how to solve the problem? There is overall problem of skill atrophy, which is possibly coming in, right? And at the same time, we are creating a large technical debt. We are creating thousands of lines of code which nobody understands and checking it in, having functionality. If something breaks tomorrow, who is going to be responsible? Nobody understands the architecture, etc. So to me, it looks like an opportunity for the compiler developer, right? So I was talking with Professor Singh. Formal verification, for example, can become very critical, right? All of a sudden, right? So if it doesn't really matter if your code is auto-generated, how the programming language looks, can we introduce more information in the language itself? Can we introduce mechanisms to capture intent of the program? Basically, if you look at it, when I write an optimization or try to do tuning of a heuristic, I'm trying to correlate the programmer intent, saying that this is what I want to do with the hardware and trying to optimize it. But now the programmer itself is telling me, okay, this is what I want to do. So can I capture it better in the language itself, right? So can we simplify, right? So can we add extra components if it is going to get generated at the time of generating the code itself? So far the problem was, okay, people said, okay, I know what I'm writing, I don't really need, if you want formal verification, somebody goes and extracts the intent and does it for me. Now you are generating the code. So you can embed information in the languages to extract. Can we have compilers who do the vulnerability detection by default, right? So instead of saying that do it as an afterthought, you do it as part of the process. Can we have a good cyclical loop of, okay, LLM is doing development, languages are helping it, compilers are working together, and then have a full feedback loop, right? So saying that, okay, whatever information is generated by the compiler, can it feed back to the LLM, can it feed back to the language to improve it further, right? So these here, and I think any questions?
Any questions? Yeah, Mike, please.
Hello. Thanks for the nice talk. I had one query. Could you explain what exactly is PTX and what PTX enables?
Okay, so PTX is parallel thread execution. It is portable instruction set developed by NVIDIA for NVIDIA GPU architectures, and it enables programmability and portability across architectures. So once you write a program which targets PTX, it can work for multiple GPU architectures.
Is it a binary that is generated?
It is not the binary. It is ISA, virtual ISA, which is for NVIDIA architecture, right? So, which get then finally compiled to architecture of your choice.
Compiled to a binary.
Right, compiled to a binary.
Thank you.
Next question. All right, person in the back. Yeah, Mike.
Hello. So you talked about formal verification mechanisms. So simplifying the formal verification mechanisms. So are there any current mechanisms that you are currently employing for formal verification?
No, I don't think so. We have used, say, a live group at a much lower level. So to say that, okay, this is how you need to go and do that. They will come and ask me, why do I need to do that? Nobody, it makes no sense. Right? It kind of gives us more control over what we want to do. It is going to be open, so people who want to adopt it can go and adopt it. It's going to be open standard, so that should not be a problem.
Let's take a question from this side also.
Thanks, Shekhar, for an excellent talk. Question is, you talked about the brittle heuristics, but your machine learning algorithm is also brittle and programs change as they are
architectures, loops, they slightly different loops. Okay, so for example, on the GPU, what we would want is large chunks of continuous code. So we would want to unroll more to extract the parallelism. So for example, I will be able to schedule better if I have a larger basic block in my code, right? So I want to, on the GPU, I want to do more unrolling to extract more parallelism, to extract.
Right? So, you see, the impact and the strength of a keynote goes by the number of questions that are coming up. So I see that the questions are flowing in, but in the interest of time, I'll stop here. Please take it offline. And let's thank Shekhar for an amazing talk. I'm really sorry for the others. Please take it offline.
Good morning, and it's a privilege to speak in front of legends like Professor Debugger, my friend Krishna, and industry experts like Divindu, At the same time, it's quite frightening also. But I'm not worried because my very own professor Govindrajan sir is along with me, so all the questions, all the tough questions are very redirecting to me. So, who am I? I'm the first person on that list. Towards the end of the talk, I'll tell you where the second author is. Before I start, okay, so what do? We are a small team which does open source contribution to Eclipse compiler, Eclipse ecosystem, and Eclipse Java compiler to be precise. And we'll talk about the ecosystem and what is there and what we do. But before we get into the agenda, I'd like to express my immense gratitude to two people. Some of you might have worked with him, Shrikant Areyavagan, who is a compiler expert, who used to work with IBM, currently is in Advantest, and Stefan Hermann, who is a commuter from Germany. Yeah, so the agenda is something like this. To put things in perspective, we'll talk about the holistic picture of where the compiler stands, and we'll talk about some specific issues what we figured out in the compiler. So when I speak of compiler here, I know many of you think about code optimization, GPU, binary sector, but this is not what I'm talking about. I'm talking about the Java source to the JVM bytecode conversion, which is essentially an IR for the conception of the JVM machines. How many of you use Java? Oh, very nice. And how many of you use Eclipse? Okay, fine. So how many of you use VS Code? Very nice. Let me tell you a secret. VS Code uses the Eclipse Java compiler internally. So this is what you get in Eclipse. We also have dark theme for all the VS Code enthusiasts. And underneath, it follows a plugin architecture. It's a very old software, as all of you know. And so, pardon for this non-AI, old style architecture diagram. It is taken directly from the manual of Eclipse. And all the Java features are provided by the green color one. So our team works on the Eclipse SDK, and a few of us work on the green colored part with Java development tools. So what do we provide? We provide, so it gets released every 3 months, like most of the industry standard. And we provide like completion, debugger, formatter, many of the things which you already expect from IDE. We also have disassembler and AST view, abstract index view, etc., which people use for various developing various software. So you also should understand that Eclipse is not just an IDE. In IBM itself, we have 100+ products which are built on top of Eclipse. And across the different car companies, many of them have take the UI away, take the base part, and then they build software. It's still running. Luckily, automotives don't change as fast as phones, so we still have the software running. We still get support calls for that. So what do we provide in Java? So this whole thing is provided by Java development tools by an underlying architecture which has a bottommost foundation layer, and which provides 3 pillars, as we say, which is called the Java model, which models a text program into something very systematic, but a little less than an AST. AST provides fully resolved types and stuff like that, and a Java search. So this is not a typical text search, of course, it's a type-based search. So when you look for reference of type, so when you change something, it has to go and figure out where all the types are, and it has to change that. So those code refactorings are provided by these things. So what's the bottommost layer which we are more interested in? That's our compiler. So I see Oracle folks here, and every time when we say about Java compiler, the question what I get is, okay, so how do you make use of Oracle Java compiler? We don't make use of Oracle Java compiler, it's our own compiler. So, and it follows a traditional compiler flow compiler pipeline. We have a scanner and there is a parser. It provides an abstract syntax tree, which is the place we operate on. Then we do a walkthrough. Every cycle is a walk across the abstract syntax tree, declaring its type information and flow information, etc. And we give out errors. Then the code gen here is again to generate a class file. This class file is in the JVM specification format. That looked very nice, but actually what happens is all of these things do take APIs from different stages of the pipeline. So parser, the search does a lot of stuff beforehand, so that when you do a search, it's become the searching is faster, and so on so forth for the other part of the pipeline. We also provide ECJ. How many of you use Java C compiler? Java C as in Java C in the batch code? Oh yeah, that's nice. So equivalent to Java C is the ECJ, but that's the batch compiler what we provide. I know all of you who use Java knows that a lot of new features are coming in, so it's record patterns, etc. And this is a slide I should not be showing here to a lot of compile experts here. So what do? We take a Java, a compiler, and compile to X class. But we also do errors. Now, why errors are important from an IDE perspective is that becomes part of an API. And it is on that error sometimes the tools get hooked onto. For example, if there is an error, if there is a quick fix thing, it's on that error that gets fixed on, and say that if this error comes, then you are given different choices of converting or refactoring that code into something else. So there's a problem or there's a challenge when you have not a standalone compiler, but a compiler tied to an IDE. So these are the different features that has come up across different releases. And as we all know now, Java is on a 6 month release cadence. Earlier it used to have 2 years, 3 years, etc. Now every 6 months we have a Java release. Anyone knows what is the latest Java release? How many of you would know? 25 actually. That was released 10 days back. So, which is a long-term support LTS version, which means that we support it for longer. In every 2 years now we have a long-term support version. So these are some of the latest features. I'll let you decide what is the greatest, whether it's the greatest or not. So we'll just get into the compilers, which is what is inside. So initially, so we know that class is a reserved keyword, we know int is a reserved keyword, right? And then we had something called the where was introduced. So which is also is not a keyword, but the point is the where can come in most of the cases where the type is allowed. And then we let the compiler figure out what the type is. We essentially let the compiler infer the type. So that was one feature that was provided. And it was the where was of course used by many languages, but it was also told that not many people would use where as a type, but people were surprised. We found issues where people have actually used where as a type. Now, that was not the problem. The problem was it's contextual. So where the orange one is supposed to be a contextual keyword, the other one is supposed to be a normal identifier. So but we also had this one where they said no longer you can use it as a type. So this was an error which was to be thrown, but this proved to be a blessing in disguise for us because we still kept the compiler and we flagged it at a later stage of the compiler, saying that okay, I'm supposed to tell you that this is not a type at the parsing stage itself or scanning stage, but I'll tell you at a type stage. So we created a special type for where, and we flagged it at a later point in time, and we used it for further processing. Suppose where comes in a place of in the place where a type is there, but it is not supposed to. For example, if there is no initialization, we cannot do a type inference, so that's an error. And this is a proof of the stack trace to show that it is indeed the error has been flagged there. So we thought we were very smart in solving that issue until Java guys had different ideas. So this is on 1.8, this is section 3.9 of the Java language specification. You can see that it's just keywords. But this is what we release in Java, the same section, Java 25, which was released 10 days back. So you can see that so many contextual keywords that has come. So some of these contextual keywords can come in something called module info file. So that was pretty easy to solve, because if it's a module info, then we know it's a keyword. Most of the cases except transitive, I think. But then other things like users, other things like yield or non-yield, those things, permits, all these things are having the same issue. It can come as a restricted identifier as well as a normal identifier. So then we looked at some of the. So why is that a problem? So any questions on this theory of LLVM, you know whom to ask. So don't ask me. So we have a java.g file for grammar, and we use something called a JIX parser generator, which is LLVM. So and then we got a parser.java on which we operate upon. So we need to. The grammar has to be a LLVM, in this case it was not. Then we looked at the history, and in 1.8 when we implemented lambda expressions, we faced a similar problem, and we were not able to differentiate the so to resolve the conflict, we had to add a synthetic token, and then you make the grammar context free. So this is what we did. We stopped at it. We did a Vanguard parser, and then spawned the intermediate. We spawned the parser, and then we reached an intermediate code and figured out the right code. So now, since we have a hammer, we solve most of the problems using this. So this is one thing. One problem what we had is the scanner parser independence is lost, because you stop the parser, you stop the scanner and get into a spawn parser stage. But it works. We are looking for alternate seat. Now I just have less than 5 minutes, so I'll just go through some of the problems what we faced. The other one was statements. Switch statements now can be a switch expression. So statement does not have a value, expression had a value. So we had a lot of optimization that was going on. In fact, these were not equivalent, because the default was not there in zero in the statement, but in this case it is there, because expression has to have a value any point in time. So while statements you can just skip. Yeah, so we had to, of course, the synthetic grammar token was introduced. Then we had to introduce a secret local variable, and there was another problem with about code verification, because in Java we do it's a stack-based machine, and we have to, instead of just the instructions and operands, we'll have to add operand types as well. So we had a lot of issues on that. Then there was type switches. Now, why is this a problem? Because you know that for the normal, let me just go through this. In the normal switch, in the bytecode, you can see that K0 is K0, case 1 is 1 on the bytecode also. But in the type switches, we need to transform the type into a case constant 0, 1, 2. For that, we have to now get into the JVM and take the information back. And if you really look closely, you can see an implicit loop that is there, because you're going back to the switch, top of the switch expression. And then came records were manufactured a lot of code. 2 more minutes. Okay. Yeah, I think just close. So Java comes up with preview features, which is like, they're not fully features, they collect user feedback. So the problem is the transient feature that can throw away. But from our perspective, we follow a single grammar, and the same grammar we have to make sure that both of these things work. The backward compatibility, which was a problem. And now all these things are fine, but it's like we have a lot of offline features up above. I'll just skip this in the interest of time. So, I just want to leave with the thought that if you are only looking at the compiler, it is like a solo journey with a patch and every feature looks like a solo journey. Well, you are free to do. By the way, that's my fellow my co-author, so he's happily riding away. But actually what's happening is we are in an integrated journey. We are traveling with grandparents, old features. We are traveling with new features. We have to take care of that. And probably in a car, where if the relationships are API, the car gives the guardrails in the sense that automated API tools to check that whether we have backward compatibility, are we setting up the right versions, etc. And it's a nice journey that takes forward further. Thank you, and we have. We have a lot of challenges. Anyone is interested, and they're interested to contribute. Let's talk. Thank you.
Thank you, Manoj, for taking us through the journey. We may not have gone through the full journey, but some ups and downs definitely. Some questions. Let's see. All right, we'll start. Manas, go ahead. Yes. May I request Suchishmit to set up the next things?
Thanks, Manoj. This is Manas from IT.
Yes, I know.
So on one extreme, I mean, this is about many of us who write static analysis for Java. So on one extreme, we have tools like Suit and Tai and evolve very slowly, right? I mean, a newer Java feature is released, we don't have static analysis supporting them. On the other extreme, we have Java C that's not very conducive for writing static analysis. So you talked about the AST. I wanted to tell you, ask you if there is support for data flow analysis, a control flow graph, getting the current class hierarchy so that we can do interprocedural analysis, etc. in ECJ. If not, is it on cards, for example?
Okay, so first of all, we don't do any code optimization, unfortunately, but we do provide the framework for, as you mentioned, we do have type hierarchy, which is in AST based. So there are ways by which so the compiler AST will keep it sacrosanct. So we provide a DOM AST, on which we provide a lot of tools. Well, you can do code walkthrough, you can do you can decorate or whatever. So you can do flow analysis. We of course do some flow analysis, especially for some basic flow analysis for the code generation part, and also to flag some of the basic errors like the variable not initialized, etc. But there is support.
Yeah, go ahead, second.
Thank you for the nice talk. My question is that when you say these APIs, are they adhering to some protocol like LSP? And my second question is, the parser you talked about, is it error-tolerant parsing and incremental parsing at play in the background?
A good question. Answer to this is the first question. The LSP comes at the level of. So LSP is a language server protocol which is used by the VS Code, which takes the JDT and gives out the JDT LS. So there is, if you go to the Eclipse project, there is a JDT LS project, which is essentially providing the LSP implementation. On top of which is a VS Code connect that is happening. Okay, so this is the level below that. And to answer your question on incremental compilation, yes, that is provided by doing hooking onto the resource change, and the parser will do an incremental change on that. So for that, we do something called a working tree instead of the normal just the AST. So that change the working copy. See, and there is a incremental change that happens.
So the parser is written in such a way that even if it has syntax error, it anyways generate a partial AST, or?
Yes,
it is, because see, that's the whole point of an editor, where you need to provide completion, which is essentially a partial tree.
All right. Let's. There are further questions. Please talk to Manoj. I'm sure they're around. Let's thank Manoj. The next talk will be given by Suchishmit, which is a senior engineer at IBM ISL. He'll be talking about optimized Ghash intrinsics.
Very good morning to all. I hope I'm audible. And definitely my video is on here, so not to worry. So I am Suchismit Roy. I am from IBM India Software Labs from the CTEP department.
Hello.
I'm joined by Saurav Kantishyam, who is the co-author, and he's also part of IBM India Software Labs CTEP department of IBM India Software Labs. So as a part of CTEP department, we work on different compiler optimizations as per for different tool chains like GCC, OpenJDK. So different tool chains, we try to optimize it as per the platforms that IBM supports. So that's just a brief of what we do at CTEP. And before I start, I would really like to thank each one of you for taking out time on a Saturday morning and attending this talk and showing your interest. It really shows your passion and interest towards this field, and I really appreciate that. It gives us a lot of energy to come here and present as well, and this will be an ongoing trend. So with that, I'll start my talk. So we're presenting our work, Optimize GHash Intrinsics for OpenJDK on PowerPC. So I'll give a brief outline. So what I have tried to do here is that I have tried not to just bombard you with the paper, and because this was more like a research paper that we submitted, and it has all these graphs and figures and all that stuff. So I'm trying not to bombard you with that, but I'll try to build the story to this work, because the work is just that we did some optimization, but we have to present the story. Then you will be able to understand the work, and we'll try to present it in a way that when you read the paper, it will be a breeze for you. You will be able to relate with it a lot easier. Yeah. So what is the motivation of this work? Why did we approach this? So the paper is the what and how. Okay, but before we pursue any work in life, we have to be very clear on the why. So what was the why here? So we have this OpenJDK repository. So when we run Java we are supporting, Java is supported on multiple platforms. So for PowerPC, we did not have a native implementation for GHash. So I'll cover what is GHash. So, but basically you just assume that GHash is a very computationally intensive algorithm that is present, and we did not have an optimization or native implementation on PowerPC. By optimization I mean, so in Java we have all heard about just-in-time compiler. So when you run a code like 1,000 times, 20,000 times, there are some warm-up iterations. So when you run it like 10,000 times, then what the JIT does that, okay, this code is being run so many times, let me see if there is a faster implementation on this. And then it switches to your native implementation. So for PowerPC, we did not have that. It was just a ghash.java, simple Java code that was running. So it was just a scalar implementation, which was giving huge runtimes. So customers were complaining that, okay, when we are running this security algorithm on PowerPC, it's giving huge runtimes. So that was the motivation behind this. Basically, in Java, there's an annotation @intrinsic candidate before a method, which tells the compiler that, hey, this one can be optimized. If it has a native implementation, go ahead and use it. Okay. So I have used the word intrinsics. So what exactly is intrinsics? Basically, I'll tell you in very simple terms. So we all use different APIs or methods in Python, Java, etc. So let's say you're doing a length of a string. So in Python, you do len of string. Okay. So maybe there is a better way of doing the string length, but you do not know what is the existing. Like we are not sure what the assembly implementation is. We are just trusting it to do something. So I'll give you a general example. There are two routes to go to my office. Okay, and one route I am very confident because I've stayed in that area. So many of us will have this experience. We know that this route is the best. Okay, but so for some reason the Google algorithm was not picking up that route. So when the Uber Auto is coming to me, I am telling him that please take this route. But he's like, no, the Uber app is suggesting me this is the best route, so I will take that route. So what, I am at the mercy of the driver. Whereas if I have my own vehicle, I know which is the best route. So I will take that route. So intrinsic is this thing that it is giving you a finer control. Like you know that this instruction is there in the hardware. This is better to use. I do not want to go by what is being implemented. So it gives you that finer control as a program. And that's why we keep saying C++, C, they are very fast. A lot of juniors ask me, should I start learning with Python? I said never. Always start with C, C++. Because Python, it gives you all this API. Yeah, one guy agrees with me. So it gives you these easy things to do with, but you will never know what is happening under the hood. because see, as a programmer, we have to understand. I mean, if I am somebody who is just making an ML app or something, or an app developer, I don't need to know the details, okay? But if as a programmer I have to go, it is essential that you start with these low-level languages. Okay, you can skip assembly, okay, I understand that's frustrating, but you can still do with C, C++, it's like one level before that. So that was just a little bit about what is intrinsics. Okay, before Ghash, I'll just explain this attack scenario. So, how many of you have heard about Ghash? Okay, how many of you have heard AES? Right, okay, I wanted this, okay, great. So Ghash is the next security layer after AES. So we all know over the internet, everything is encrypted. Okay, WhatsApp also gives you all these things that everything is encrypted. Everything is encrypted, and that is true. So we are definitely ensuring that whatever we are talking on the internet is encrypted. If somebody tries to tamper, if somebody tries to sniff the packets and try to find out what we are talking, nobody can find that out. So AES has done this job brilliantly. Okay, so there is just one caveat it misses. We do not know if the ciphertext is modified. Okay, so let's take one example. Let's say this is the altered message. Let's say the message is the same. Okay, so in XOR property, if you do the XOR of the message, XOR of the ciphertext with the original message twice, and the message is the same, you will get the original ciphertext. So this is what happens on the receiver end. Now what is the vulnerability here is there, and it's not an easy vulnerability. You need a skilled attacker for this. What I will do is that I will guess what the message type is. Based on that, I will only modify certain parts of the ciphertext. It is not a straightforward attack. It will require a lot of effort, but a determined attacker can definitely do it. So you can actually guess. So these areas are just zero. Okay, so we are doing XOR with zero, so we'll just get the original part. What we are trying to do is we have to guess the message format and exactly make some ciphertext changes. Okay, and this won't happen in one attack. Initially there will be some garbled output because I will not make correct guesses initially. That will lead to garbled output. What will happen is that the receiver will reject those requests. Okay, but in these kind of cases, if I successfully able to change parts of ciphertext and I make this 10 to 100, so then the receiver can accept. Receiver can accept it. There is that possibility. Now you can say that we can make the web server logic very robust. That okay, if somebody is ordering, we actually check whether it's the right order, whether the price is right. But that would mean continuously I have to check with the database and all. Why I will take that overhead when we can avoid this beforehand? Okay, so here in this case it's like 10 cappuccinos, you ordered 100. So somebody can alter it to 100 and the barista will come up with 100 coffees. So it's something like that. Now imagine how catastrophic this can be if, let's say, you're ordering something on Amazon. Somebody knows the exact message format, because in Amazon and this header format, it's like a predictable format. You know what the message format is. Order this, order on Big Billion Day, order this for this. Okay, so you can change the price. And if there is no web server logic handling that, okay, is the price correct or not, then what? You end up paying more. Okay, so that is a possibility. And also, let's say you are talking on Slack with your coworkers, your manager is giving you a deadline of 5 days. Somebody can change it to 1 day. So, GS can save you from overwork as well. Okay, so this is the overview. So as I said, AES, we know that the confidentiality is assured, but Ghash is that in addition to that, what Ghash is doing is that it is able to detect tampering of the ciphertext. So we have a subkey that we are generating from the AES, and we take the message, and then, as you can see from the ciphertext, we are generating this. We are running the Ghash algorithm, and we generate an authentication tag. So at the sender end and the sender end, the authentication tag is generated, and on the receiver end, we run the Ghash again on the ciphertext, and the authentication tag is regenerated. So if the authentication tag is if they do not match, then we just reject it. Okay. So this part is called authenticated encryption. So encryption, AES is doing your encryption, but authenticating that encryption, that is where Ghash comes in. And G hash is just hash, of course it's just a hash. G stands for gallery. Why, I'll tell that later. So this entire process is called, entire algorithm together is called as AES GCM, that is AES Galloy Counter Mode. Okay, so this was authenticated encryption. Now let's go to what is field arithmetic. Okay, this is very interesting. When I took up computer science in class 12, I thought I will never have to touch maths again, and here I am. Okay, so, and it's interesting, this field was taught to us in group theory in mathematics in second semester, and I never understood what was the application of it. So, by definition, it's a mathematical structure where you can add, subtract, multiply, divide, and we have an additive and multiplicative inverse. So, this add and if you can add, then you can also do a subtract. Basically, you do A plus B, and if you have to subtract, you do A plus minus B. That with that you can generate your subtraction operation. So that's fields. So fraction is a field. In fraction, you add something to 0, you get back the same element. So that is its additive inverse. Multiplicate and so that's its identity element, and when you multiply fractions, the inverse would be that the denominator goes up and the numerator comes down. This is just a general example of fractions. In integers, however, if you just take integers as a field, let's say you take the integer 2. If you want to find its inverse, so the identity element is 1. If you have to find its inverse, it will be 1 by 2. So now 1 by 2 is a fraction, it doesn't belong to the field. Okay, so then we cannot make a field out of integers. However, we can make it into a field and a finite field using integers modulus prime. So imagine like you have different times spread out. You are making it a circle. So now you have a limited structure, and on that you operate. So that's why it's a finite field. So and we have to work with finite fields because we have to make predictable reversible math. By that I mean we have a field of suppose 5 elements, and at the encryption we do some element, and decryption we should do an element. We should have an inverse of it. Without the inverse, at the decryption we will fail. So that's why we work on these fields like integers modulus prime. Okay, and this is one example for modulus 10. This 5 will not have an inverse. So basically, if it doesn't have an inverse, the decryption will break. Okay, now polynomials. Why we are choosing polynomials here? And this has brilliantly been taught by the mathematicians. And I also wondered. So what they did was they smartly found the similarity between binary polynomials and prime. So we saw integers modulus prime, right? So each prime, we can represent each integer as a product of primes, unique primes. Like if you have 6, you have 3 into 2, unique representation. Polynomials has the same property, irreducible polynomials. Okay, so you can factor the polynomials and you can get the unique representation. Then they went a step further. They took particularly binary polynomials, coefficients of 0 and 1. What happened with that? Now I just have a field which has bit stream. Once I have the bit stream, I can easily operate it as a programmer, and I can leverage the CPU architecture, perform different operations on it. So that was the thought behind why we use polynomial field. And Galois field, GF stands for Galois field. Galois field works on this kind of fields. In brief, this is the different operations. You can see this, in the interest of time, I'll just explain the example. So you can see this x power 3, x squared plus 1, this is the binary stream. X squared plus x. Then adding polynomials is similar to XOR, and when you multiply, it is a left shift by k bit. So as you can see, x power 3 into x squared, this is degree 5 polynomial. So you see that this bit is set. So this is similar to just doing a left shift operator. Okay, so now we understand what is the algorithm and why we do G hash and everything. Now, but where is the optimization? This is where the software and hardware comes together. So we saw an optimization using data parallelism in vector architecture. So let's say in G hash we operate in 128-bit subkey and 128-bit messages. So let's take this simple example. You have 70 people. Let's say you have 128 people. You have to transfer them using a car. Car can handle 4 people. Okay. We are not taking extreme cases. There will somehow stuff people in. People will comfortably sit. So we have 4 people, and that would need multiple trips. The car has to continuously keep going and coming and bringing people. Okay. These multiple trips is basically going to the memory and fetching the word. Going to the memory and fetching the word. Whereas you have a bus, you put everyone at once and it's done. This was done for traffic congestion. So similarly, in vector architecture, we can actually leverage this. And to also do this, we need a concept of memory banking. So basically, if you have 4 people coming into a bank, if you just have 1 counter, you cannot parallelize it. So you need like 4 counters. So memory banking helps with that. This is the instruction that we have used in the IBM architecture, which is BPA, polynomial sum double word. The data type was double, so we use double word. If it is byte, we also have instruction BPM sum B. So according to the data type, we use different instruction. Okay. Karatsuba multiplication won't cover this much. Basically, instead of doing 4 partial products, we reduce it to 3. So multiplication is big O of n squared. Karatsuba is big O of n power 1.59. And I always wondered, how does it matter? It matters now. So that 0.5 difference can make a huge difference in these kind of algorithms where there is so much multiplications involved. Yeah, so this is the final results. As you can see, we achieved so speed up of 4x. And these are the green ones is using the intrinsic, and this is comparison to the scalar implementation. So as a systems programmer, this is our basically this is our job. We have to understand the algorithm and at the same time understand the hardware. So in any from professional setups also, I feel software and hardware teams must be the best friends. So that is when you can grow as systems programmer and also as hardware developers. So thank you.
We have time for 1 or 2 questions before we break for tea. Questions? No? Okay, yeah. Question in the back. And then, yeah. Please introduce yourself. Yeah, go ahead.
Hello, I am Omkar. So, good to see that someone is in fields and combining with software and hardware. So the question is, can like the number of multiplications you need, does it depend on the cipher?
No.
So
it's just a generic, like you don't have to consider polynomial, just integer multiplication also if you do. We used, if you use Karatsuba way of doing it, it will reduce the number of outputs. It will be more additions, but multiplications will decrease.
Yeah, question in the back, yeah.
Hello. Hi, thanks for the wonderful talk. So, like in the beginning of the talk, I was actually thinking that you actually went through all of the trouble and wrote all of the assembly steps yourself, like all the handwritten instructions in assembly for this Gash intrinsic. But yeah, towards the middle, you actually explained the VSX extension. So my name is Tatsad. I actually work in the IBM Z. So we have something called the message security assist extensions, which have all of the cryptographic assembly instructions, so that we can directly use them instead of doing handwritten assembly. And I was wondering whether Power also had something similar. So
yeah, I'm jealous of you guys because we have OpenJDK for Z, and the programmer who works for Java on Z,
yeah,
he used that
-KIMD
-KIMD instruction, which does this entire thing.
Exactly.
Yeah, for which I spent a year and I'm coming here.
Yeah,
Power, it did not have it before, but in Power 12 we are having this instruction. It is coming up. But so in OpenJDK we were doing Power 8 and above support. So from 8 to 12 there was no implementation, so we went with pure implementation.
All right. Yeah, so basically my question was, can you give me some implementation level details, like how exactly did you go on about it? Because I also work in the Golang compiler, and we are also looking into doing something similar, like exploiting the hardware accelerated assembly instructions instead of the Golang implementations.
Let's do one thing. Please take it offline. Okay, you can have tea and continue the discussion.
Okay,
Let's
sure.
thank Satish Smith for answering this question. Right? So this is Krishna Nandiyara and signing off.
माइक का स्पीकर आ हेडफोन आ माइक हॉर्न मार रहे गिटार मार रहे bro. वनीला ब्रो हाँ हाँ सो हेलो हाँ 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 ಇದು ಔಟ್ಪುಟ್ ಇದು ಇನ್ಪುಟ್ ಅಲ್ಲ ಇದು ಇನ್ಪುಟ್ ಹೆಡ್ಫೋನ್ ಯಾವತ್ತು ಇನ್ಪುಟ್ ಮಾತಾಡ್ರೆ ಮತ್ತೆ I check 1 2 3 1 2 hello 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 mic check 1 2 3 hello 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 1 2 3 4 5 6 7 8 9 1 2 hello 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 yeah.
Right? Hello everyone. Request your attention please. We are starting with the next session. We request you to settle down. Making the announcement again. Requesting everyone to please settle down. We are starting with the next session. Thank you.
hello 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 Requesting everyone to please settle in. We'll be starting with the next session shortly. And the next speaker, please come up. And yeah, please. Hello. Anuj.
Hello, welcome back to the session. So the first talk will be ELD, Embedded Linker, Why Another Linker by Parth Arora from Qualcomm. So requesting Parth to set up. Oh, okay, thank you.
Hello. Good morning, everyone. Thank you for being here. My team primarily works on linkers and more code generation tools. Here I am joined by co-author Rishabh Ali and a few more members from my team. This talk introduces Qualcomm Embedded Linker EID. In this talk, we will see what is a linker, how is embedded programming any different than general purpose programming, and how ELD meets the challenging demands of embedded programming. At the end, hopefully, if we have time, then we will see official comparisons across major linkers focused on embedded programming. So let's get started. For most users, a linker is a large black box that pops up every of the build step and takes too much time and drains all the memory. And while that is true, the story is a lot more than this. A linker at its core is a tool that takes in object files which are compiler generated and then combines them together into a final output image that is ready to run on the device. To create the output image, the linker does various operations, including merging input sections to output sections, connecting symbol references to symbol definitions, and aligning addressing. We have various open source tools available, um, including GNU Linker, that is the current gold standard for embedded linking. You also have Gold Linker, that is a faster ELF linker by GNU, that is sadly now deprecated. And we also have LLVM Mold and a few more important linkers. In its overview, it is not clear how embedded programming is different from general purpose programming. To understand and appreciate why embedded linking deserves special attention, we need to first understand what exactly is embedded programming and how it differentiates from general purpose programming. So let's see. Fundamentally, embedded programming is about programming for a specific hardware. There will be no OS or a nice runtime layer involved. Embedded programs controls memory layout, signing, peripherals, and everything else. Embedded devices are all around us. Timers in your washing machine, ships in refrigerator, and uh, and the cars. It's all embedded. They are typically used in they are typically used when the task is specific and the goals include low cost, low power, long life, and high reliability. Now let's see one key area where embedded programming is different than general purpose programming. To meet such low cost, low power, and tiny demand, embedded devices typically contain low compute resources, require complex memory layouts, and are consist of heterogeneous memory. By heterogeneous memory, I mean that the device consists of multiple different kinds of memory, including fast and slow memory units. This is very different from what general purpose program is used to. That is a huge, nice, cozy virtual memory abstraction given by the runtime. Now, with the heterogeneous memory, the complex layout and more resources, the simple task of aligning addresses becomes significantly more complex. Now, suddenly, the user has to think about what goes there, what to put in fast RAM and what to put in slow RAM. Mm. You often need to decide which feature to keep and which feature to discard due to having limited memory. As a result, embedded projects typically consist of very complex memory layout, and as a consequence, they often need functionality, features, and diagnostics to analyze the layout when things do not go as expected. A linker is responsible for aligning addresses and the layout. So, a good linker for embedded development often provides features to fine-tune the layout. For example, here's the linker script. You can see a linker script is telling how to map input section to output section and how to map the output section to memory DRAM. Some more areas where embedded programming is different than general purpose programming include they often need specialized needs like overlaying. Uh,
To use same memory region for multiple different data. Imagine having two variables at the exact same address. And they often need things like RAM, ROM patching, security features like embedding hashes in the image itself for cross-checking, and so on. Uh, to summarize, the three key features that embedded linking needs is fine-tuning the layout, more diagnostics and functionalities to analyze the layout, and third, support for custom features in the toolchain. Now let's move on to what is ELD, followed by why ELD for embedded development. ELD is a GNU-compatible ELF linker. It is designed to be a drop-in replacement for GNU. It is right from the ANSI linker project. It was initiated by MediaTek a long time ago. ELD provides out-of-the-box support for common targets used in the embedded development, including ARM, ERA64, Hexagon, and RISC-V. We support most of the common linker features, including static linking, partial linking, garbage collection, GNU command line options, LTO, and so on. Now let's see why ELD for embedded development. So we discussed the three key features required for embedded linking included the functionality to fine-tune the image layout, detailed diagnostics and analysis to debug images when things do not go as expected, and control over linker over the image. ELD also provides detailed documentation and linker FAQ examples to help users understand the linker behavior. It is things like why linker assigned this address to this section, or why linker placed this section to this segment. It's all documented in the FAQ and the documentation. With ELD, we have no mystery. Also, for third key feature of linker plugins, customers can customize the link behavior however they want. They have complete freedom and complete responsibility to go with it. Like LLD, ELD supports reproduce functionality that is very helpful when changing a bad build across teams. Now let's see some of these key features in a bit more detail. ELD provides highly detailed map file. A linker map file describes the image layout along with section and symbol information. It is critical for embedded programming. A good map file can save hours of debugging time. ELD map file is especially detailed. It provides information about linker stats, input file information, plugin actions, and so much more. It even enables debugging for linker expression that no other map file does. And this map file can further be customized using the option map detail. For example, we can pass show initial layout to map detail, and then it will print layout before and after the plugin modifications. Similarly, we have the option show symbol resolution that describes why linker shows a particular symbol in symbol resolution. Additionally, we provide extensive trace options. So unlike LLD and GNU, where we only do trace symbols, in ELD we can trace linker scripts, garbage collection, plugins, and so much more. Next, we look at the linker feature that allows you to add any feature to the linker. For example, let's say you want to warn users if garbage collection is not enabled. Plugins can do that. Or maybe you want to change the layout, for example, to change the ordering of the layout depending upon section names. Plugins can make it happen. Or perhaps you want to store and compute the image static redundancy check hash as part of the link itself. Plugins can do this too. Plugins can completely customize the link, but beware, with great power comes great responsibility. Now let's get a sense of how ELD plugins work. and how to use and create them. My colleague Resha will go in more detail here in the later presentation. So in ELD provides hooks and linker wrapper APIs for people to write plugins. So ELD provides hooks at key stages in the link pipeline, and the plugin defines hook handlers while using the linker wrapper APIs. And then the ELD calls the hook handler definitions at the hook sides. For example, here we are seeing a simplified link pipeline which consists of init, reading input files, rule matching. In this step, linker matches the input sections to the output sections. Then we have section merging, where linker merges the input sections to output sections. And then performing layout, where we assign the addresses, add trampolines, and do so much more. Then at the end, we have writing output image. So for this, we will have hooks like act before rule matching, act before section merging, and so on. The hook names are intuitive and they indicate where they are placed in the link pipeline. One thing to mention here is, in ELD, the plugins are first-class citizens. Mapper document the plugin actions to help debug the plugin produce a bad layout, and reproducers account for plugin files, plugin configuration, and everything else. So it all works seamlessly. Now let's see some more use cases of plugins. Plugins can be used to create complex image layouts, such as section budgeting and PGO-based placement of sections. Plugin framework can enable things like LTO linker scripts, though this may involve some compiler changes too. It can be used to speed up link time by adding caching layers in the linker itself. Moreover, it helps to keep linker simple, slim, and easy to debug, because custom functionalities can stay in the plugin itself. For example, let's say if you need some proprietary linker feature, then it can stay as a plugin, but linker will be open sourced. At Qualcomm, we have many plugins downstream. Lastly, we will see target design in ELD. ELD is designed in a way it is easier to add a new backend to the ELD. Typically, oftentimes the linkers have linkers are filled with if condition throughout. That's if arm then do this, if risky then do this. In ELD, we simply define a new class and implement the virtual functions. The common functionality stays as it is, and we target deviates. Then they have to define the new class. And it is simple and relatively less error prone to add a new backend to ELD. Now let's compare linker features across major linkers. Since we lack time, I will summarize the list here. So currently, GNU linker is the gold standard. It provides very good support for linker scripts. It even has plugins, though they provide less functionalities than ELD, but the design is there. Where GNU lack is, one thing is GNU design is single-threaded, so it is slow by design. Additionally, GNU don't provide many tracing options. NavPy lacks things like linker script expressions, which can cause more painful to debug things. Additionally, in GNU, plugins lack many important hooks, and the NavPy don't document plugin actions. In LLD is very fast, and it is becoming better for embedded in the last few years. It lacks in a few areas. First being, LLD NavPy lacks many information and currently needs improvement for embedded development. Additionally, in LLD there is no way to customize the link. Lastly, we have Mold. Mold is extremely fast, but it don't provide any features for embedded development. There are no linker scripts, no good nav files, and no plugins. Then let's see ELD. ELD provides detailed linker scripts, plugins, and everything. Currently where ELD lacks is, ELD don't support symbol versioning.
Though it is not important for embedded development, it is important for general development in the non-embedded cases. And ELD also don't currently support target x86 64. That's currently in progress. This table describes things in more detail, but we don't have time to go through each thing in particular. Lastly, future goals. They are future goals.
Thank you for a very informative talk. So the stage is open for Q&A. So yeah. So can you please read them?
Hey, thank you for the interesting talk. In one of the slides for the plugin, you mentioned the caching of results. I think that is one of the key ideas also behind Wild, what Wild is trying to do for incremental linking. Have you actually done some experiments over here to make it possible with any plugin?
No, so far don't have plan to support. So far don't have plan to support interlinking. I think it's error-prone, and generally the pros don't outweigh the cons. So if you see in link framework, many things can be cached. So let's say few things like rule matching, it can be cached very effectively, but layout definitely not. And one small bug can destroy everything. I think caching layouts in particular, it is not worthy paying. Wild is very, Wild thinker is very ambitious in this thing, and hopefully they do it. But it's a very complex problem, which more things that is not worth solving. For example.
Yeah.
But good question. Thank you for asking.
Yeah. Thank you.
Hi.
Any more questions?
I have a question. Hi, I'm Prahlad from Metals. Just curious about one thing. I understand that linking has got a lot of system-specific functionality, like Windows linking, loading. It's very different from what happens in Linux and so on. I didn't hear you talk too much about those differences. It's purely
Yes. Linkers we don't support all format, but still clearly on Windows and Linux, but it will only create the L files. Yes. Okay. That is why we'll go into the core format and the Windows in particular.
Okay. Yeah. Thanks.
I think we can take one more question, if there is any. Okay, let's thank the speaker. There is a change in the schedule, so the next talk will be replaced by the last talk of session 4. So the next talk will be by Karthika Devi C from Qualcomm, and the title of the talk is Enhance LLVM Loop Vectorization Using Polyhedral. So I request the speaker to set it up. So the scheduled talk of this session will be shifted to the last talk. So it will be placed in the last, as the last talk of session 4.
So, hi folks, this is Karthika. I am a compiler engineer from Qualcomm. So, today I am here. the agenda. Overall, we'll go through what vectorization is and what is loop vectorizer, what is poly, what can poly do, what is its current state, and how are we planning to collaborate poly with loop vectorizer, and what is the basic infrastructure implemented, and what are the possible future goals. So first, vectorization. I know most of folks are from compiler background here, so you might be knowing, but just for the new ones and to brush up the topic. So vectorization is something which converts scalar operations into vector operations. As you see, a block on the left to the block on the right. So what are vector operations? So vector operations are the operations that happen on block of elements. Let's say consecutive elements in an array, for example. Why it is needed? Because it gives us performance boost and it makes maximum use of underlying SIMD hardware, which is present in most of the modern hardware today. And also, in general, there are two types of vectorization. One is the loop vectorization and other one is the SLP vectorization. In this talk, we'll be concentrating on the loop vectorization. So, in general, without any hints from the outside, compiler by default does the vectorization. It uses cost model to decide what loops to vectorize. Apart from this, users or developers who are using the compiler can give pragma to the loops. So these will be taken in the form of hints by the loop vectorizer and it will perform the vectorization. Okay, what is loop vectorizer? So we talked about vectorization. So this loop vectorizer is that middle pass in the LLVM which performs this vectorization of loops. So it also produces target agnostic vector code because it's a middle and IR pass. For example, something like this to this. As I mentioned, it uses cost model and it has matured over years. Like they are constantly improving the cost model for the same, and the vectorizer is becoming better day by day. And it is also capable of vectorizing like different kind of loops, which has reduction, induction, even if the iteration is going in reverse order, or if conversion for that matter. Also, it relies on the prior canonicalization pass, such as loop simplified pass. Like it expects the input to be in a certain loop simplified pass to perform this vectorization. Also, it performs this vectorization on mostly innermost loops and the ones which are straightforward memory access patterns. So, now I told about vectorization and loop vectorizer. Then why are we talking about poly? Why poly when we have LLVM's loop vectorizer? So, consider a below loop which has an anti-dependence on C array. What do I mean by anti-dependence here is, there is a dependence between C of I minus 1 and C of I. For example, consider iteration 3. So, the read happens from C of 2 and the write happens into C of 3. So, that write is again read by the next iteration. So, every time the C of I has to be written before the next iteration of C of 3 is read in the next iteration. So this is why there is an anti-dependence pattern here. So what does loop vectorizer do? Loop vectorizer rejects the above case, telling that there is an anti-dependence pattern because of which we can't do the vectorization. Now let's look into poly. First of all, what is poly? So poly is a powerful framework for geometrical representation of loop. In nutshell, we can say you can see every iteration, for example, in a loop, like as an integer point in polyhedral. It is capable of doing high-level loop locality optimizations. Also, it performs classical loop transformations, like it can do loop timing, loop fusion, or it is even capable of splitting the loops. So, the specialty about poly is it can find parallelism, means even loop vectorizer can find it, but it can find parallelism even in the cases which are not normally seen as straightforward parallel. So thus it opens up SIMD opportunity. We are going to exploit this particular feature to make use of vectorization. It also can deal with like complex loop nests and data access, which LV is not like up to the mark. So for example, we are giving the same loop to the poly. What does poly do? Poly builds scopes out of it. It understands the dependence pattern, it reorders the statement, and also it gives us optimal ordering of the instructions. So poly's output looks something like this. It's fine if you don't get the entire context. The main takeaway from here is you can see a couple of for loops existing here. So this is the output from poly. So it is equivalent to something, this is the input program we have given. So it gets into something like this. So the single for loop have been split into two for loop. How is this useful? Like I mentioned, the C of I write should happen before C of I minus 1 read every time. So this as a human we are able to understand, but Poly is able to understand this dependence pattern and it is capable of generating two different for loops. So now, since we have two different for loops, now the dependency is removed, like C of I write happens before the C of I minus 1 read. So both the loops got vectorized below and in the end we get improved performance. So like this is one very small case to demonstrate the capabilities of Poly. Now, since we know that like Poly is capable of doing things which is very useful to vectorization, what is its current state in community? It is by default disabled. If you want to enable, you can use explicit flags like MLLVM Poly. And if you want to, without profit, if you want to analyze all the loops, you can pass this Poly process unprofitable also. So also we used to have vector codegen support in the past for Poly, which has been deprecated in like less than a year or something. So right now there is no vector codegen support from Poly. So all this comes to a common point. So there has to be some collaboration between Poly with loop vectorizer. This idea has been in and out for a while, but yeah, the overall theme is Poly's analysis and transformation capabilities. If we can combine with loop vectorizer codegen capabilities, overall we get better vectorized loops and more loop coverage as well. So right now, how are we planning to deal with? We have like metadata infrastructure in the LLVM. We can use the metadata to pass uh, information from Poly to loop vectorizer. For example, vectorize enable is an existing metadata which can be used here also. Also, Poly created loops have better scheduling of statements. So apart from vectorization, it can open other optimization opportunities as well. So overall, it goes like this. There is Poly, there is loop vectorizer. We give the input IR. So Poly gives out optimally scheduled IR with metadata. Then loop vectorizer can give us the vectorized IR. So what we started doing is we try to implement a basic infrastructure. First, we have to annotate the loops which are processed by Poly as vectorizable. That is what we did. And we are using the existing metadata, which is vectorize.enable to do the same. And right now, it's a very basic step like just infrastructure establishment. So we are controlling this entire feature via Poly annotate metadata vectorized flag. So this flag guards it like only if you explicitly pass this flag, Poly will annotate the metadata data to it. You can look into the merged change in community if you are interested. So I would like to mention about the couple of challenges we faced while setting up the basic infrastructure itself. One is the multiple loop versioning and line number diagnosis. So what is loop versioning? So when compiler is not sure if it has to do something, and if it knows a bunch of conditions, if they are satisfied, you can go ahead and do a specific thing. So that is when we introduce loop versioning. So currently this loop versioning is happening both in Poly and LLVM loop vectorizer. So this is bad because it results in like multiple version of code. End of the day, code becomes very bloated. Once the code is bloated, all the optimization overheads are removed. Like all the optimization overheads are created there. So right now we try to address it to some level by, let's say, Poly is creating. So it's a creating call flow where one side is the Poly process loop, other side is the fallback loop. Right now the fallback loop we need not do anything with. So the fallback loop we are labeling it as disable the vectorization so that at least loop vectorizer won't come in and touch it. So future plan is possibly we have to go on like removing the additional runtime checks also because right now there might be redundant alias checks going on in Poly and loop vectorizer, and as we all know runtime checks are very costly. So before the patch it was producing something like this. 4 paths were taken because first split is done by Poly, then loop vectorizer comes in and splits it further into 2. So now by avoiding the fallback loop from getting vectorized, we are just at least bringing down to 3 for now. So other major issue we faced is like Poly does not have like the feature to add debug info for the loops that it created. So why is this problem? Generally, when we are doing such kind of experiments, right, we would always run experiments and see if the performance has improved and what happened. But apart from performance, there is one more metric which is called loop coverage. Like how many more loops are we able to cover now? Like what are the different kind of loops Poly is able to touch now? So to measure these kind of things, we should get proper diagnostics from the loop vectorizer.
it is not possible if poly is not appending right kind of debug info. So because of this, we are facing like loss of debug data and incorrect loop coverage metrics. So what is the solution for this? Obviously, like poly have to append the right debug info, but it's not as straightforward. Why? There is no like one-to-one correspondence. For example, poly might take one loop, it might end up creating two loops out of same, or it might end up tiling the loop. So there is no like one-to-one correspondence here. So it's a bit hard to like append debug info as such. So, but at least we are planning to add some support where we get some closer line numbers as possible, so that some decent metrics we can get. So this is all again a starting of a big work. We have like a bunch of future work in this area. So one thing is, like let's say right now we are only passing like vectorized metadata. We can pass like more like vectorization inputs like such as vector factor kind of. And apart from that, like while running the experiments like Qualcomm specific experiments, we also felt like lot of loops it's not even beneficial to vectorize. For example, the loops which have very small trip count, it's much better if you unroll the loop rather than vectorize it at all. So these kind of things like poly is not looking into right now. It will just mark it as vectorize as long as there is scope there. And also, since this is experimental work, it is important that we have much more fine grained control. Of course, we have a flag, so that flag will control things at a file level. So let's say if you want to control it at loop level, then what you have to do is you have you have to be able to annotate a particular loop telling that poly just act upon it, or poly just don't touch this loop. This loop is fine on its own. So for that, we have to implement pragma for the same. That is one scope to improve. Apart from that, just because a loop is processed by poly doesn't mean it's good to vectorize the loop. So this is where the majority of the work lies in. So the overall goal here is to improve the inference from poly. How can this be done? Couple of approaches we are taking on right now. One is by improving the front end of poly overall. For example, reduction cases were not very well covered by poly earlier. So we improved more support for the same so that more reduction opportunities are captured by poly now. Similarly, there should be other areas where poly's front end itself should be improved. Apart from that, more than improving the analysis capabilities, we should know when not to force vectorize. So you should know when to bail out. You should know when not to process further. Just leave the loop as is. So that bailout condition is more important. We have kind of a downstream patch for now, but we'll soon upstream it at some time. But this bailout is quite important because a lot of times not vectorizing a loop will enhance the performance overall. So yeah, I think this includes a bunch of possible future works, but obviously there could be more also. Uh, but that's mostly it. If you have any questions.
The stage is open for the questions. I also have one question. Sure. Is it always in poly that the transformations are applied in sequence, or it's like applied and sometimes it's applied to the
So Poly doesn't look into code in the form of loops directly. So it takes a regions, and from the regions the scopes are derived. So from the scope it takes in the order of in what order the scope has been created, in the same order it performs, but it won't be like same order as the like loops are present in the original. So according to Poly, it's more of scope level, and some point I've seen like it goes in reverse order. Yeah.
yeah. So other questions are very
Hi. So we exclude couple of things from poly. One is the transformed code itself. Other is the metadata which gets annotated from the poly side. So transformed code by default poly transforms the code. But the second one which we are annotating the metadata is more important here. And like I mentioned, right now we are only annotating vectorize enable metadata, which just enables the vectorization. So loop vector. So for example, if you give a pragma to a loop from a user side, let's say, asking it to vectorize that particular loop, how will the loop vectorizer behave that time? So respecting the user instinct. Similarly, poly will enable this the same metadata from the poly side, but it will not be restricted in future to just this one metadata. In future, we might have to add more metadata to the same. But overall, to answer your question, two things: one is transform the code by itself and the metadata.
Hello. Hello. One question here.
Hi.
So, what are the metrics or features that you see when not to vectorize?
Okay. Like different things. For example, in a, recent case, we saw when the dependence distance is very close, like 1 or 2, that time also we felt it's good not to vectorize. Like I mentioned, one more category. Let's say the trip count of the loop is very less. It's not very profitable to vectorize. So unroller will perform much better in those kind of scenarios. Uh, these two are just coming in top of my mind right now. But that be more scenarios like partial vectorization kind of places, or if the where the vectorization is getting applied and remaining scalar expansion happens. If the scalar expansion code is more laggy than the part which is vectorized itself, then also it won't be beneficial to vectorize. Yeah.
One follow-up question is, vectorize will go into multiple steps. These steps would make it more costlier than vectorize.
So I will request you to take this question offline because the time is almost over. So I will request all of you to have the speaker again. And then move on to the next talk. So the next talk in the session is by Hello Kumar Sharma. So the topic is enhanced debuggability support in the LLVM based AO60 compiler for various Fortran languages. Over to the
So, to the model.
you have to press
Yeah.
that press.
That's our source. I don't know how they are in front of.
With all people.
Okay.
You have to use both of this.
You'll have to do next from here.
No, you can use the slides.
Okay. Okay. Sure.
Do that.
Hey, hi. Very good afternoon, guys. So, when we talk about compiler,
You're not audible.
okay, when we talk about compiler, so the end result about the compiler, so it is often we think like it is only the generated code which helps, right? So in ideal world, what happens that you write a program, you compile it, and it works as intended. But in real world, it doesn't happen that way, right? So what happens like during the development till the release, there are more often failures than the success, and after the release, even if the frequency is less of the failure, but that is more costly. So in those cases, what we do, we use a magical tool called debugger. So debugger, it doesn't work on its own. It is not independent. So what is being done behind the scene is the compiler generates some debug information, and that debugger consumes and interprets your program and gives you a source level debugging. So I myself, Alok, along with Bhuvan and Ginny and Saurabh could not make to the conference. So we all form a team in AOCC who are working in all three part of this. One is debugger, second is front end, compiler front ends like Clang and Flang, those are LLVM based, and LLVM backend itself. So those three we work for debug support. So the thing is, before I go forward, I'll like to share one thing, that there are general misconceptions. There are two misconceptions I will talk about. One is that Fortran is kind of a forgotten language. Okay. Second is that art and mathematics are two different dimensions and mutually exclusive. So there is one example I will have to give you, and that will kind of shatter these two. So there is a very famous piece of art, and that is movie Titanic. So what happened after its release 15 years later, it was changed. There is one scene that was changed, and that was because at the accident date, the sky which was shown, that was inaccurate, as but the claim date and place of the accident. So, and that was actually that is very interesting, right? Art, and then it has to be accurate. So, art, A from art is actually accuracy. So, those things, one astrophysicist did this, he did and generated also. So, there is one software called Novas. I may be wrong with spelling, it is some expansion. So, with that, you can generate all those things. So, that is written in Fortran. Not just that, actually, there are a lot of things. This is art part, right? If it is math is important in art part, then when the human life is involved, it becomes even more important. Like in Japan, there's a lot of earthquakes come. So to predict that, there is a lot of complex math need to be involved. That is written in Fortran, most part of that. And in US and UK, a lot of weather conditions and all over world, those cyclones and keep coming. So this climatology and all those things, they also need a lot of maths, and they are also written in Fortran. So there is like this trend, like why those things are written in Fortran in place of C. We are compiler developers, so we are kindly biased towards the C, because that very well suits that very well suits our need, right? Because it is actually it's a difference of the design philosophy. C is designed for the very low level programming. So whenever anything, we will see in the next slides. So anything, it is very low level. It is the basic constructs are as simple as possible, so that the efficiency of the time and effort is very less. Uh, Apart from that, like exactly opposite design philosophy is for the Fortran. So Fortran's design, the C is actually rely on your intelligence of the programming knowledge. But Fortran is completely different. It targets the domain experts. So they are not very good in developers, and as you know that the information is often lost or are misunderstood when domain expert conveys that to developer, and then developer develops it. So what they do that, okay, just you just need to know the English, and I will provide you very like as you write in the paper and pen the math part, that part will be exactly same you write in the program, and half of the code I will do. Like compiler will generate most part of the loops. The loops you will see at the end generated code, those are most likely being generated by the compiler. So as against the like C and C++, there are built-in types of array, right? Array A is equal to B plus C. That way you can write like those things. A is equal to, you can assign that. So in a single line, you don't need to write a messy loop. So it has become very popular amongst the domain experts. That is why all those scientists and they like it very much. So there are multiple reasons why Fortran is being chosen. Performance is one. Writing is easy. It is very small code, and also it is maintenance is very easy. So our this thing will be like the. I will focus more on the built-in types, which will provide all those things. But other things are being caught up by the other compilers also, other languages also, because we know that one compiler, one language, actually that keep inspiring the others. So one feature comes here, and others will also getting inspired and follow that is the same path. So I will be focusing on those things, those four things. So let's see, like I will give more details in next slides. So, as I talked about earlier, that it is this is front end. Front end uh, provides some this thing. So, one thing you will notice, like you might never have noticed probably earlier, that along with code, generated code, at the very last there are some metadata part of it, and they are like you can see that left hand side everywhere it is some numbers are there. So we will call it say metadata 2030, and it looks actually linear, but what happens that when we you use an definition, if you make a link, in that case it becomes a hierarchical structure. It becomes a picture. So this is exactly and in what front end and back end do, they generate a dwarf info. Like dwarf is kind of a handshake between the compiler and debugger. So they do handshake, and they agreed upon some format, and we are using dwarf format here. So in dwarf format, you can see the same, that hierarchical structure was there in the dwarf format also. using the tabs, they do the parent-child relationships. So, and this guy is actually mapping up the main program where you have scopes, that parent-child relationship scopes are there, and uh, and it also like you can see the tags, like you can see every node is a tag. It is child of some parent, and every tag inside it has some attributes, so which gives like debug information filled with that. It will have some addresses, its name, and some linkage to some other part, like say for variable what type it is. That is once that is fed to GDP. GDP is able to provide uh, the source level debugging we are used to see, right? So this is the behind the scene thing which happens behind the scene. Okay, so the thing is because LLVM is a evolving compiler, so for that sake, what happens is like C and C++ is more towards the system, so its debugging was already there. But for the photon debugging, it was in very bad shape. You can see that the thing I was talking about, the how we define array in C, it says array and 10. So 10 is what? It is actually hint to the compiler that okay, this much memory you need to allocate. And its range is actually 0 to 9. So they just note those two things. This was there, and for that, like you can see the second picture. First picture is a program. Second picture, there is a local variable called ARR and composite type. It's the tag which defines this variable. In that you can see its basic type is there, which is some integer in this case. Last is elements, that is a list of elements. So in this case, because this is single dimension array, we have a range of that is count. So count was enough for fulfilling the C's needs. So it just needs like how much allocation I need to do, and the same thing you can see below it generated into dwarf. You can see that sub range array type is there, and the subrange type is there. So just keep this thing in mind. Any changes, any modification we will be doing in the subrange, like subrange type in dimension thing, that will come in subrange type. Apart from that, the high level things that will come in array type. So we will just keep, and similarly in LLM IR, it will come in composite type, whatever comes in array type, and subrange will be mapping to the subrange type. Oh, okay, okay. So of late, C and C plus also have a variable length array. You can see here, like it has a variable length array where it can be in place of constant, the variable is there. Just see here, the downside it is in subrange type is count 17. 17 is some variable, it is pointing to some variable linked to metadata 17 is there. That said, that whatever is in IR, it given there, DI subrange, it was having count, and that was from IR, and it was a mandatory field. It has to be there, of course. And optional field was lower bound because for the language defaults, and C always had 0, so you can escape it. That's why you don't see it here. And that gets converted to dwarf. Okay, then we come back to Fortran. So Fortran also has like in real life, what happens that uh, 0 to this thing, that kind of ranges are not there in real life. Like see, if someone is there, like some employer is there, what he will be interested in is like maybe 18 to 60 is range it will be interested in. So what happens? For that purpose, we need upper bound and lower bound as a primary property. Uh, Out of three, upper bound, lower bound, and count, whatever, if two are available, that can be calculated. But if we don't do that, then it will either be, we will first store in count, and then later debugger will expand do the calculation. So compile time or run time complexity will increase, and debugger will be less responsive. Second thing is like there is some explicit shape array. This and yeah, with debugger earlier it was not working, but now it started working after those changes. Like we have added fields and worked on that. One more thing in this thing, Fortran, we also have outer bound, it can be shown as star, that I don't know, it can be anything because it is outer loop. So it can be optional now. So that change we had to do. Okay, so one thing, like there are other thing also, that a very good example, very good thing in Photon is that you can use the array sections. Like you can use in the same array, you can use odd elements in one thing, using the two as a stride, and start point something G or something, and even elements in some different this thing. So what happens that if you pass that from array, then inside that memory locations are not contiguous. They are actually index will be 1 2 3 4, but it will be because passed from outside. So one way is that you can use the work array, but that will spoil the automation. So you need to have this thing called array descriptor, that will also become the primary property and address of the actual allocation. So here the top level header size, it will have the array information, top level information, and dimensions will be having for each dimension, lower upper bound, those things offsets, and those offsets we know that those can be mathematicalized. Like you can, for any given dimension, you can use that. But they assume shape array, the same thing. Top array extension can be passed. For this purpose, what we did we added the data location for the actual thing, and the second thing we started using. As you can see that because this mathematics is, for that there is a support for the LLVM, and there also there is a support for expressions, like dwarf expressions are there. Only thing is that this push object address we need to uh, insert, so that that can that can take the actual address, and you can see that it started working. Only thing is that for allocatable arrays and uh, other array, uh, the pointer array, we also need to, because in the whole within the scope also it can change. So we for validity purpose associated and allocated two fields in LLVM was added, and that gets converted to corresponding dwarf. And you can see that when it is not allocated, it is showing the right state in debugger because of this. Assume as well as assumed rank is there, so for that a rank field was added, and generic subrange, because you don't know that how many subrange you need to generate. So generic subrange we did, and in along with that, because debugger internally what it does, it runs a loop uh, for rank, and that iterator being passed to this dwarf stack, and to get that we used DWOP over. That support was added. With that, it was assume chat rank started working. So these things is what we added. It's not just that. But in string is very important, because in C, for represent the string, what we do, we use the null character at the end. What happens, like if you somehow mess up, so it will keep on reading the character unless it crashes, and if that is even like you will be still lucky. But what happens, like sometimes it gets some wrong null, so it will behave something like very bad, like you will not be able to know. So that what happened wrong. So this thing, like in Photon, what happened, that it added the length as the primary property, so of the string. So with that, what happens, that if single string is there, and with that, like you can also you avoid the null thing. Apart from that, what happens, that substrings you can use, like you can say that 0 to 10 this is one string, and 11 to 20 this is another string. Module debugging was there. Just 1 minute more, I will tell. So for module debugging, it was not working because the file line was, that is not important. Second thing was that because of the, to avoid the conflict, uh, we use the renamed use of the modules from somewhere. So for that, what we were doing is, like we were using all the variables which were in module, and we were saying that okay, the name was available only when the name was renamed. So but that was eating a lot of space. So what we have did, we have that, see, imported module is there, imported declaration is there. So if we make use of the parent child relationship of it, the top level important module, it will be there. Only things which are getting renamed will be available there, so it saved a lot of space for us. name list is the last, and after that I will stop. So name list is actually very wonderful thing that okay, I will just later note I will say that okay, there's a databases and we read and write to the files, and what we do like in real life, what happens that sometimes it is difficult to differentiate the account balance versus the age, right? Such kind of things do happen. So what happens, they Fortran provide something like name list. So name list, they are like you group the number of the variables, and using the name list you read and write. So those mess up will not happen. Uh, the acknowledgement for to Saurabh and Eric. With that, like those things are already available in LLVM, GDP, and we have upstream also. And along with like any new front end can make use of that. Like LLVM Flying is now making use of that information. And with that, I will stop. And sorry for taking this more time.
Thanks for enhance reliability support in Fortran. So the stage is open for question and answer. Yeah. Is there any questions?
Thanks, sir, for the talk. I was wondering, like, so all of these are adding dwarf support for Fortran, right? Like, because most GDB also supports like custom printers. For example, if you have got any, if you've got if you got pointed to any memory location, you can say that how the struct is laid out, and we can have custom printing printers. Like one of the examples you showed was printing arrays of like custom lower and upper bounds.
Yes, yes. So your thing is limited to array, or your question is limited to array or name list? You just can. Hmm.
My question is, can you add like could it require like all of this had to be in dwarf, or could this have been as a printer for GDB?
Actually, that will happen. Actually, it is about like I'm talking about source level debugging, right? I'm talking about source level debugging, right? So because Fortran has something like that and inbuilt support inside the compiler, so you need to have a source level debug support. For that, you need to generate enough information that GDB can rely on and can read the information, give you this thing. So your thing is like, why not everything can be inside GDB itself, inside of the compiler, right? That is what you are saying. Yeah.
I think what support is the compiler providing? Like,
Okay.
how can like, for example, to take a specific example of printing array and
Yes. Yeah.
so if that can that be implemented as a custom printer for GDB? Like,
No. Actually, the thing is, GDP is not able to do everything on its own. Like
you add like custom dwarf symbols?
no, dwarf is fixed. Like for a given version, dwarf 4 or dwarf 5, dwarf is fixed. What we need to do, we need to make compiler to generate that. So because a lot of those things are not used in C, and it started, this evolving LLVM started with C support. We need to give the information, because on its own, how can GDP will understand that is it a array location, or there is a descriptor? Like it cannot differentiate, right? That what is its description, right? Is it an array section, or is it allocatable or something? So you need to give some information to GDB. Few things it can do on its own, like define and all are there, right? You are talking about that. You can define a thing and then do it things in GDB itself. But unless it knows about the actual thing which source level developer has written, it will not be able to tell you, right?
I will request other people to just take it offline. So sorry for this. So please take the questions and
Sure. Thank
request
you.
Alok to kindly answer them.
Sure.
Thank
Thank
you.
you.
So we're next talk. So how can we by Pankaj Dhoni welcome. And that talk is open source compiler for vendor specific risk V extensions. Yeah. So I will request the speaker to set up.
it has a caller. Is this what?
Okay. Hi everyone, this is Pankaj. So I develop compilers for RISC-V based microcontrollers. So there will be some element of that touch of RISC-V in this talk. So what I'll be doing is I'll take you through the journey of how we move from a downstream compiler to open source compiler. So basically we have, I think all of us have worked on downstream compilers which conform to some proprietary IC. Now, let's say you have a downstream compiler, it works, it gives you the expected results. Yeah, yeah, okay. Uh, so you have a downstream compiler, it conforms to a proprietary IC, and you are getting the results. This compiler is in production. Why do you want to change to something upstream or let's say open source compiler? So this is a big decision, and we have to do it in collaboration with the processor architects and the compiler team. So processor architects have to give a statistics of whether you can get a ISA which functionally overlaps with the downstream ISA. And the second part is you have to also get the same KPIs which you are getting on the downstream ISA. So if those two requirements are met, then yes, you can take a decision to move to a upstream compiler or upstream ISA. So here I'm taking an example of RISC-V ISA. It can be any ISA you might be aware of. So another challenge when we move to a upstream compiler is you would have a lot of custom algorithms you would have developed downstream. So how to move them upstream? That's the second challenge we have to look at. So can we have can we have open source ISA and still develop downstream? Yes, of course you can do that. Many of the companies do that. But what are the problems if you are just developing downstream for an upstream ISA, for example? So it limits your potential to scale for size and performance. Essentially, you started getting diminishing returns. You put optimizations or after optimizations, but then you are constrained by how much you can achieve. Also, you need a larger engineering team in terms of you need experts actually because uh, they have to understand the code size and performance benefits, the algorithms. So you need some expert locally. Imagine a new person coming in, a new member in the team. You have to have a ramp up time for him as well if you are doing it downstream. Another part I think is the ecosystem in terms of like you develop your compilers, whether it works or not. Generally, if you have a downstream one, you end up creating your own simulators, runtime development. So what we came up was a solution of using something called as a RISC-V ISA. I don't know how many of you have heard about it. I think it's popular. So the interesting part of RISC-V ISA is it is modular. So you can use subset of extensions and combine it with something called as vendor extensions. So and this need not be part of the overall RVI. You can just propose it and you can add the support in the compiler. So we would be looking at this. We would be looking at this ISA where you have base components from RISC-V and you have two vendor specific extensions. For example, this XQCI and QCCMP. I'll go in some details about what these are. So let's say we decided on moving to this ISA. So what would be the design approach we would take? So one is finalizing the ISA, which we did earlier. Now we have to understand what a processor architect should do and what compiler team should do. Now you will think like why a processor architect is important. It is very important, of course. He or she is very important because it's a collaborative task. You can't do just like I'll develop my own optimizations and not think about the instructions, right? So that we we have to work together. So the processor architect's role is to evaluate the application code, understand what instructions can go in, for example, this vendor extensions, and then our flow of regular compiler design starts, adding assembler support, instruction selection, and adding the backend passes. And the interesting one here is this linker relaxation. So in this particular methodology, what we had observed was there are challenges in terms of finding the encoding space because you are trying to put uh, everything, your vendor extension in a open source ISA. So you have to find space for yourself. Another challenge is by you when we develop something from scratch, it's easy. Accommodating in something existing is difficult. So that's one challenge we have to look for. Then there was one interesting thing which we observed was related to this introducing symbol relocations and relaxations in linker. So this is the overall approach we will take, and I'll go with all these details for each of the blocks. So one of the vendor extensions which we introduced was this XQCI. So I is simply integer, QC is Qualcomm, so it's that simple. X is for any vendor extension, you prefix it with X. The primary purpose of this is to get performance and code size on microcontrollers. So basically, if else kind of code is what these instructions will be targeted for. So if your input code as if else kind of C code, then your instructions would be like, so for example, conditional, or you would have some other different instructions which improve the code density. So these are some of the instructions categories which this vendor extension has, and like what we would, as a compiler engineer, what we want to do with respect to this instruction. So we want to see what how well we can use this instruction. So for example, we have this 48-bit instruction. So uh, how well can you use it so that you can save those 2 bytes? That's something as a compiler engineer we have to think about. For there are this load store multiple instructions. So we have to think how we can use well. For example, uh, we can replace this memset with just one single instruction. So this is one of the areas we have to keep thinking about when processor architects adds these extensions to maybe any vendor extension. Then this is a another vendor extension XQC CMP which came up while we were discussing. So with the processor architect, so there was a fundamental problem found out while with respect to debugging. So there is existing extension ZCMP, but there is a problem with that the frame pointer is not at a constant offset. That creates a problem of unwinding the stack. So we proposed a new model where the frame pointer is at the constant offset, and you can easily like debug the program. This has just 6 instructions, but they are very powerful. So when you enter a function, you generally save a sequence of registers, caller and callee save, and then you allocate some stack space also. So this extension enables you to do it in just one instruction. Similarly, when you exit the function, you can re, uh, remove the registers and deallocate the stack. So this is a very powerful extension, and we proposed an alternative to that to accommodate for debugging. So as a compiler engineer, what are the takeaways for us in this? So you have to understand how you insert a prologue and epilogue for each function when you are dealing with this instruction. So that's the understanding we have to get. So now coming to how we will design the compiler for this. So as I was saying, these are vendor extensions. So they'll RISC-V vendor extensions, though. So obviously they'll go in RISC-V backend. So we'll again go through a typical flow of adding assembler support for them, adding the instruction selection patterns, adding some backend passes, and then finally relaxations. Relaxation is very native to RISC-V, is what I have observed. Like when we were doing downstream compiler, we didn't had this linker relaxations. So I'll talk about that also, why it was so interesting. So with assembler support, you will just add the XQCI and XQCCMP instructions, for example, these vendor extensions, and you will try to reuse the classes. So as I was saying, it's always easy to create something new. Add to something which is existing is always difficult. So you have to reuse the operands, you have to reuse the classes. So that's sometimes it can be a challenge. Then the next part is when you are adding the instruction selection pattern. So we were looking to add compressed patterns. So compressed patterns is about like selecting a smaller instruction. If you have, let's say, a 32-bit instruction and you also have a 16-bit instruction, so you want to select that. So we can do it with compressed patterns. Then, as I was saying, there is a challenge for compiler engineers when we move from a downstream compiler to upstream compiler. We would have our own custom passes. How do we add them to a existing backend? So in our case, this was some kind of a pass where we combine multiple load stores, uh, sequence of load stores to a one multi-load store instruction. This is something we are still working on to understand how we can add to the existing RISC-V backend. Then the most interesting is the linker relaxation. So we have symbols, we have functions, but we will know about the addresses of them only at the link time. So you can do a better job at the linker when you do it with linker relaxations. So we were able to come up with some non-standard extensions to the ABI document. We have introduced around like 5 relocations and around 11 relaxations. They are very powerful. We got around like 4 to 5% of benefit just from that one flag. So the takeaway from this is like we can leverage on the upstream uh, optimizations for, let's say, in this case, LLVM RISC-V backend. And what I enjoyed most was the collaboration with community and the feedback. We develop downstream compilers, but we are like, oh, I'm the best, but there are better people to understand our code. So the often overlooked part of whole compiler development is understanding how to verify the correctness of that. So with, let's say, if you have a upstream ISA, for example, RISC-V and upstream compiler, you get many things for free also. People are interested to contribute to them. So in this case, I'm trying to demonstrate this QEMU. So we didn't have to do much and we could get the QEMU working, and we were able to verify our extensions with that. So takeaways are you have to first evaluate the open source ISA, whether it overlaps, and you have to identify the vendor extensions you want to provide, instructions in that, collaborate with the processor architects, understand the existing backend if there is something, and try to include the assembler and maybe backend changes there. Again, there is last part is importance of validating whatever you did. And Yeah, I am open to take the questions. Thank you.
So we will go for questions.
My name is Abhinav. My question is very simple. As frame pointer here is constant memory address. They are very big. So let us assume we won't make a memory more vulnerable and enable exploitations as frame pointers as constant memory allocation.
Okay, that's a good question. So, it it make it vulnerable? I'm not sure.
Because actually, this is the way why RNA in the concept came for the dynamic linking purpose. So
Hmm.
that vulnerability can be avoided by binaries and PI binaries tools.
Uh,
And pick binaries mostly.
Correct, correct. So in this case, the main objective we had was with respect to debugging. That aspect, I think we have to look at. But it's
That if you use abstract binaries and other things, it will help.
correct. That's there. So that maybe it has to come with some more instructions. So which we have not explored much. Thank you, but that's nice question.
So we'll take the next question. If there is any. So, yeah.
So the third bullet in takeaway is the importance of validating the compiler things. I was curious how you do that.
With Chemo, sir. With Chemo, yeah. So there is one company called RevNG. So they have included the support for this vendor extensions in their Chemo. It's upstream. But what they did was like they made it more generic so that any vendor extension can be tested in that Chemo. So they have created a nice generic framework.
So I think we don't have any more questions. Let us thank the speaker.
Thank you. Thank
For
you.
the nice job. So this was lunch now and this number. So further announcements will be made by the volunteer. Thank you.
So, few small announcements. So, lunch will be served both excited. Later, let me volunteers tell you where to go. Also, also we have a set left side to my left. If you want to picture yourself and your friends, do that. Take yourself, never talk to take pictures. And we have a lost phone. Somebody please come up, and if it's your phone, you can claim it. And before the speakers for the next session after lunch are after you're done with the lunch, please come to the front so that you can check your slides. We also have the job board set up. You can go check that out. Thank you.
Just a minute. We back by 2 p.m. One more thing, we count for setup for good. I would request the people sitting on this side, please move to my right hand side for the lunch, and the people sitting this side move to the left side because here we have one counter, and this side on the right we have two counters there. So please distribute it then.
ट्रांसमीटर को इसको सपोर्ट करेगा ना इसको वो चेक कर इसमें ही कर लेंगे फोन में करना है क्या कैमरा में करना है कि फोन में करना है कैमरा इफ यू कैन डू इन कैमरा बेटर होगा हाँ बेटर होगा तो मेरा काम ही नहीं देखो वैसे इतना चला है ಯಾವ್ದಕ್ಕೆ ಕ್ಯಾಮ್ರಾ ನಾನು ಇದು ಬೇಡ encoder.
plus plus, right? IDE. But I was very young. I assumed that the language that I was programming in is like perfect and final, right? Just like the mountains and rivers that we see around us are. But then you grow up and realize that, okay, mountains and oceans and seas also change over millions of years. Programming languages also evolve, right? But it's just very hard to see how they evolve. So the talk is more of sort of a way for me to give some more information on how the evolution happens, right? What are the forces that is driving this evolution? So that's basically the point of the talk. Um, I have worked on a few languages. I worked on OCaml for the past decade. So I will base my observations specifically on OCaml. How many of you have heard of OCaml? Oh, a lot of people. Okay, I will tell you about why OCaml is so good. Uh, so it is a functional first programming language, but it has multi-paradigm support as well. So it has a wonderful object-oriented system. It has imperative features. You can just write programs that look like Fortran in OCaml. Right. One of the reasons why it was designed was to help engineers write Fortran code in a high-level language. It has what is known as a static type system. So and it has type inference as well. So you write your programs, types are automatically inferred. There are lots of advanced features which are liked by industrial users. I won't go into all of them, but recently it has obtained multi-core support and support for effect handlers, which I will touch upon later during the talk. So OCaml produces fast native code, so it can compile to x86, ARM, RISC-V, etc. It can also compile very nicely to JavaScript and WebAssembly. So one of the OCaml is a pioneer here. So WebAssembly 3.0 spec was considered complete few days ago, and that brings in garbage collection as a feature in WebAssembly. And OCaml is one of the languages that took advantage of the garbage collection feature as the first language. Right? Bunch of platform tools, editors, build systems, all of them are there, and the company works on making sure that these tools work. There is an ecosystem of very well written but small package ecosystem. You will find it's not as large as Python, but it's small and we like it. There are a bunch of notable industrial users, some of you whom you might recognize from this slide. So one of the big reasons why industrial users like OCaml is what is known as its high dynamic range. OCaml is great for writing lots of things, including scripts to large-scale scalable systems. A lot of the people here may build research prototypes in OCaml, but a lot of people also build production infrastructure in OCaml. So here are some examples. So OCaml is a language that is tailor-made for writing compilers. Hack is a language from Facebook, Meta, right? So Facebook app is written in this language called Hack, which is a statically typed language on top of PHP. And the compiler for Hack is written in OCaml. The first version of the Rust programming language was also written in OCaml. And the WebAssembly reference interpreter also happens to be written in OCaml. So if you want to contribute to WebAssembly, you have to write some OCaml, right? OCaml also compiles to JavaScript. So there is this very big SEO tools company called Ahrefs. So they write all of their front ends in OCaml and compile to JavaScript, and that's what they deploy, right? So it's a great language for writing web front ends as well. If you use Docker on Mac or Windows, the reason why Docker for Mac and Windows app works is because OCaml. So it's the reason why you can run Linux containers on non-Linux hosts. So there is a very nice paper that will be in ICFP, International Conference on Functional Programming, on the experience report around this. I encourage you to have a look. We also launched OCaml into space earlier this year. So Parsimony is a spin-out of Teradis, where it's building this operating system for space. And we launched a little CubeSat with some OCaml code running on it in order to manage containers in space. And it was launched on a SpaceX rocket. So some OCaml code that I wrote is running in space now. OCaml is also great for writing correct code, right? So it's heavily used in finance. One of the big companies that use OCaml is Jane Street. So they have 60 million plus lines of code in OCaml. They write all of their systems using OCaml, right? From large scale trading systems to the UIs that the traders use to even writing FPGAs, right? So they write OCaml code that runs domain specific programs on FPGAs. So they do deep network packet inspection for the packets coming in from the network, and all of that is also written in OCaml. Just an illustration that you can do lots of things with OCaml. But you'll be surprised to hear that OCaml is 29 years old. I'm assuming that it is older than many of you in the audience here, right? Just to drive the point home, this movie was still running in the theaters widely, right? I was corrected on Twitter. Somebody said, look, this movie is still running. So it's not a surprise, right? But yeah, it's OCaml has been around for a while. And this was the best-selling phone, right, when OCaml was released. But we are still relevant, right? We are doing interesting things even now. So how is this possible, right? So OCaml 1.0 was released in 1996. And even that time, a lot of the features that industrial users like is already present in the language, like the fast native backend, low latency garbage collector, and the module system. But really, the history goes much, much longer back. So the ML in OCaml comes from meta language, Robin Milner's meta language for writing proofs in LCF theorem prover, right? And even at that point, we had this wonderful type system and type inference run. So we are basically inheriting all of that really hard work. And this was inherited by Guy Cousineau and their group who implemented a new intermediate representation called CAM. Stands for Categorical Abstract Machine. That's what the CAM in OCaml stands for. And O was later added. That was the object system. So that's how OCaml came to be. But OCaml is still evolving. So 2012 saw OCaml 4.0 get released with GADTs, and 2022 saw OCaml 5.0 with multi-core parallelism and effect handlers. But if you sort of look at this, there is 50 plus years of steady evolution of ideas, right? And there is 30 plus years of code that is out there, right? And the question is, how do you thrive, not just survive, after 30 plus years? So one of the secret sauces that I think OCaml has is that it's very simple and stable language. So OCaml won the SIGPLAN Programming Languages Software Award in 2023, and Xavier Leva, who is the creator of OCaml, gave a nice talk about why OCaml succeeded. He mentioned a lot of reasons. One of the reasons he mentioned is that the language has a very simple cost model. So it is easy to just look at the code and say how much time and space the code will use, right? And the compiler produces efficient code that almost looks like the source code that you've written. It doesn't do aggressive optimizations. But the nice aspect is that if you want to optimize something, you make a small change in the code, you will see a similar change in the generated code. So this is a very nice aspect for industrial users who are trying to build code that they understand. Right? The other thing that is very nice with OCaml is you can take code from 20 years ago, and it is very likely that if you take the latest compiler and compile the code will compile and run, right? I often invite my friends from the JavaScript ecosystem and hey, have a look at this wonderful language. You should play around with this. First thing they will do is they'll go to our package manager repository and see that most packages are not updated for 6 months. And they will say, look, the ecosystem is dead, right? Because in JavaScript, you have to keep updating things all the time. In OCaml, the truth is that these packages are good enough. They've sort of reached a plateau where they are good enough. They will continue to remain good enough. You don't have to do anything to make these packages continue to work, right? So, but of course, I want to acknowledge that there is a trade-off between simplicity and stability and innovation and growth in the language ecosystem. And OCaml is squarely on the simplicity and stability side. So if you use OCaml, you may consider that compared to other languages as a conservative language, and that's by construction, right? We like to be conservative in this space. So a bit more on how the language development is organized. So there are 27 maintainers today in OCaml. They come from various parts of the world.
France, UK, Japan, India, and USA, across industry and academia. But the point to note here is that these are all volunteers, not I would think that not even one of them is paid to work on the compiler itself. So they're all working on something which may be related to the compiler development, and they volunteer their time to maintain the compiler, right? Like I do. My job allows me to work on whatever I want. I choose to pick OCaml to work on it. Um, and the other point I want to make is that they are not the people who are designing how the language should evolve, right? They are basically the custodians of the compiler. They sort of decide what features get into the language, but not the ones who are deciding what features should get in, right? So who decides that? In the rest of the talk, I would like to convince you that you can contribute to the language, right? So there are various models of language evolution. I sort of tried to box them into a few groups. So OCaml and Python are what are known as user-driven. So as a user of the language, you can be like, look, I want this feature. And then you can propose this feature. You can implement this feature, send a PR to the language. And if it is good enough, you will just accept it, right? This is quite different from committee-driven development of C and C++, JavaScript. Um, there are other languages which are committee driven as well, where there is a standards body which sort of says, here is how the committee should be. These are the people who are on the committee. They decide what the language should do and how it should evolve, right? And there is this intermediate model, which is WebAssembly, where it's open on paper. Anyone can go and participate in WebAssembly community groups. You just have to send an email and you can go participate in the discussions. But at the end of the day, WebAssembly is implemented by major browser vendors. So these four companies, literally three now, so they can sort of decide that you have to have their support for a feature to get in. And if they are not convinced, your feature will not get in, right? So that's a sort of behavior there. And the other point that I want to make is that there is no separate language and compiler in OCaml. So the C language you can go and buy from the ISO website. You can pay 25,000 rupees. You can download this document which describes what C language is, and the compilers implement this language. In OCaml, there is no separate language, right? Which whatever language the compiler accepts at a release is the language, right? You can sort of view this as the bar is lower for the change to the language. If you have a good idea, we can just include it in the compiler, and when we release the next version of the language, that's your feature in the language. So how is the process organized? It's an open process. All the communication, all the development happens on GitHub. So all the PRs are public. There is no private repo for maintaining code and having discussions. This often comes up in the community. Hey, the maintainers have this separate channel which we don't know of where they're making decisions. There is no channel, right? There is a mailing list. No mail appears on the list. When a mail appears, it would be like a blue moon, right? So nobody sort of looks at the mailing list at all. Everything's open. You can go read the PRs, issues, RFCs on GitHub. The evolution itself sort of operates in this multi-speed model where if you have a small fix or an improvement, you can make a feature request or open a PR, discuss and get that merged. So one thing that we do as maintainers is every PR needs a maintainer's approval before merging, right? That's the only, but we don't have to, we are sort of vouching, putting our mark on it. We don't have to be the person who sort of has closely reviewed it. We're sort of stamping our approval on that. But when you have large features, it gets complicated. I'll talk about one large feature that I worked on. So this may need bespoke ways to handle this. So it may need publishing papers or extensive performance evaluation, mechanized semantics, and whatnot. But the point I wanted to make is often small features, presumably small features, take a lot of time, much more time than expected. So we'll see one example of that. So OCaml does not have the equivalent of C++ vectors, where you can add an element and the vector grows, right? So it only has arrays which are fixed size.
and a student observed that, okay, this feature is not there, let me add a feature. So the process is open. So they added a PR saying, look, here is a feature that I implemented. So there was a lot of support for this feature. So we want this feature in the language, but the implementation itself was, there was a lot of room for improvement. So the maintainers decided, okay, we'll have to discuss this later. So we'll close this PR for now. And then it took a long time. So 2022, another expert in OCaml, who is also not a maintainer, came in. They worked a lot on cleaning up the API. So they developed a clean API. They put in a lot of effort. So the code was much larger now. But we discussed this a lot, 92 threads on this PR discussion, 92 comments on this thread. But there were concerns around multi-core safety and performance. So we discussed this for a couple of months, and we said, okay, we need to separate this out, the API question from the implementation question. So what we decided was we'll open a separate PR just to discuss the API with a naive implementation so that the API can go in. So it went in again after 10 months of discussion, right? You can see that the conversation thread there has 342 comments here. It's keep on growing, right? But once this PR, the API PR was merged, it was easy to get that optimized implementation in. So that was merged May 2024. If you look at the summary of this, this feature was proposed in 2019 and merged in 2024. Initially, it was 200 lines of code, ended up with 2,500 lines of code eventually, right? 500 plus comments in various PRs. You might wonder whether all of this effort is required, right? And as OCaml maintainers, we believe that yes, it is, because we are, if you write code today using this dynamic arrays feature, we want it to work for the next couple of decades, right? We are not thinking about short timescales. We are thinking about code that will survive for 10, 20, 30 years, right? So we believe that this effort is necessary. And the other point is that it is much harder to undo changes after they have been made, right? So once you release a feature, people depend on it. You can't undo the changes very easily. So we are very careful about letting features in. The larger change that I would like to talk about is multi-core OCaml, which adds native support for concurrency and parallelism to OCaml. There are two separate features called effect handlers for concurrency and domains for parallelism. I'll spend a little bit of time on effect handlers later. So I led this project, so I had a chance to closely observe how this evolved. So I would like to share some lessons from that. So let's start with the challenges, right? So when you take a sequential language and make it multi-core, in a garbage collected world, you need a multi-core garbage collector. You need a multi-core runtime system, right? This is like taking a car and replacing the engine with a new one, right? And you need to somehow make the language itself thread safe. So languages like C, C++, and even Go, when you have a data race, you don't have any semantics. Your programs can do lots of fun things. I mean, crashing is good, right? Leaking passwords is bad. They can do that, right? But OCaml is a safe language. So when your program compiles, we want the programs not to crash, not to leak your passwords, not to do other, open up to a huge wave of security issues, right? So we needed to come up with semantics for the language itself to have this notion of what is safe and unsafe in a multi-core setting. And the biggest thing is, I mean, I'm under no illusion that just because we have this multi-core feature, everyone will start writing multi-core from the day it is released. 99% of the code will still remain sequential, right? And we need to cater for those people as well. In a way, if you have a large 60 million line code base, and I said, look, you can have this multi-core feature, but you have to change all of your code. That's not going to work. So, and I also want the performance of the sequential programs to remain the same on the parallel runtime. So we had a very strong goal towards maintaining feature and performance backwards compatibility. So one way we were able to do this is by building credibility by publishing key results and performing continuous rigorous evaluation. I'll tell you a lot about that later. So we started out in 2014. Our idea was to take the upstream compiler, fork it into multi-core OCaml, continue to develop it, but also downstream
changes from the upstream compiler. And after a few years, we'll be at a stage where we are happy with how it evolved. So we will slowly upstream changes back to the mainstream compiler. So one of the ways by which we built confidence for this very large feature is publishing papers. So OCaml comes from this lab called INRIA in France, which is an academic research lab for computer science research, right? They value academic, or OCaml's roots is also a lot in academia. We value academic research a lot. So publishing papers brings in a lot of credibility. And the way it brings in credibility is that it's not just reviewed by the maintainers, it is reviewed by the wider community of experts who know how these things work. We published a bunch of very nice papers. I'm not going to depth into each of these, but for developing the compiler, this was important for us, right? Publishing results and getting them accepted was a way to unlock the door to get the feature into the compiler. I will dive a little bit deeper into one of these features which I worked on. It's called effect handlers for the concurrency story. I'll spend a little bit of time on this. So I want to define concurrent programming as, in a very, very broad sense, it's a place where computations may be suspended and resumed later, right? Many languages provide concurrent programming mechanisms as primitives. So you might be familiar with a lot of these. I am not. But the observation here is that there are lots of these mechanisms which are very different. But you will also observe that there are languages which have more than one of these in, right? JavaScript has async await, generators, promises, callbacks, and so on. And it's not impossible to sort of have your end application use many of these together. So the semantics of how these interact is unclear, right? And these are not like formalized in any, I mean, these are hard to formalize generally. So, okay, so we said, look, we want concurrent programming features in multi-core OCaml. How do we go about it? Which one of these different features do we pick? But we decided we are not going to build a zoo of primitives for OCaml. We are not going to add all of them, but we want the expressivity, right? Expressivity is a very loaded term. I'll try to dig into what expressivity I mean is. Really, what we want is that we want the smallest primitive that can express many of the concurrent programming patterns. There are lots and lots of patterns. We don't want all of these to be implemented. We want many of those to be possible, right? That's our goal. And we ended up with this feature called effect handlers. Effect handlers are a mechanism for programming with user-defined effects. So they come from category theory, which I don't understand anything of, but they offer a very practical way to build modular and composable basis of all non-local control flow mechanisms. What does this practically mean? These mechanisms that we sort of saw in the previous slide, where there was a huge list, you would be able to implement all of them as libraries on top of this one primitive, right? And now if you are able to do that, the advantage is that in order to reason about their interaction, you just think about them as, okay, this feature is implemented as a library on top of this core feature. So I can understand the implementation interactions by their translation down to this core feature, right? So that's the promise, right? And from an operational standpoint, effect handlers are first-class restartable exceptions. So I assume many of you have programmed with exceptions. If you have the ability to sort of go back to the point of raising an exception after the exception was thrown, but also have this feature as a first-class feature, which means you don't have to immediately do it. You can do it at a later point in time, right? So keep this idea in mind. It will become a little bit clear. But for those who've studied continuations, all we are doing is structured programming with delimited continuations, right? You don't need to understand what delimited continuations are. I'll walk you through with a couple of examples. But the real power is that they enable lots and lots of nice programming models. So you can implement probabilistic programming, reactive UIs, resumable parsers using this one feature. In fact, a feature called React hooks. How many of you program in React here? Okay. Are you aware of React hooks? Yes. So that is directly inspired from this feature, right, in OCaml. I don't understand React hooks, but it sort of has this flavor that it is sort of seen in lots of places, right? So some OCaml code. It's okay if you can't read OCaml. I'll walk you through this. So what we're doing here is declaring a new effect called E, which when performed returns you a string value, right? Don't think about any other syntax. It's like an exception declaration, but we are declaring an effect. We have a notion of a computation which is run within this try with block. It's your try catch block in other languages. There is a notion of a handler which is like your exception handler, but it's a special one. We'll come back to that as well. With an exception, you can raise it. With an effect, you can perform it. And performing an effect suspends the current computation. And what it does is it operates after that like exception handler. So it sort of unwinds your stack, tries to find the closest matching handler, right, where the exception is handled. Here the effect is handled. So this E here is the effect that you are raising, and that is handled here. But in addition to handling this effect, you get this wonderful thing called K, which is called as a delimited continuation. Essentially, think about that as the rest of the program between the point where you perform the effect and this handler. So it sort of suspended your execution between those two places, right? Now you have a handle over this function, which you can resume using this continue primitive. So you can go back to where you left off. Now you carry this additional information that it's a string, right? So we declared initially it takes a string. Now I can resume that with a string. Okay. This is all a lot of syntax. Let's look at how it actually works in practice. So I'll walk you through the same example, but what I'll do here is on the left-hand side, I have the code. I'll show where my program counter is. On the right-hand side, I'll show how the runtime system is actually implemented that enables effect handlers to work, right? So I have the stack here for the main function. My stack pointer is at the bottom. My stacks grow down. So when you enter the effect handler, the first thing that you do is to allocate a little piece of stack somewhere else called a fiber, and you establish a parent pointer from the current fiber to the existing one. And this fiber is just a piece of stack with the handle attached to it. There is nothing else happening, right? This fiber, this piece of stack starts off very small. It starts with 128 words, right? It's not like an 8 megabyte stack that you allocate. And you start executing. I print 0, and then now I'm just before performing this effect. So recall that performing an effect suspends the computation. So how are we going to do that? We've done the work already, right? We've sort of split the stacks already. So all we do first is we allocate an object for this continuation, and we make it point to this fiber. And then we do the usual thing that exception handlers do. Look through your dynamic context to find the matching handler. My matching handler happens to be in the main stack, right? Over here, right? So my control switch is there. But now I already have the pointer to my suspended computation over here. And what you do is you start running the effect handler. So now you print 1. Now where are we? We've suspended, and now we are just before continue. Continue is where we can resume our suspended computation. If you sort of look at this, we need to go back to where we were, right? So I have a pointer to my stack. I can attach this, I should attach this now. But the first thing that we do is we zero out this continuation. We sort of erase the pointer from the continuation to the stack because our continuations are one shot. So if two people resume the same thing, then bad things can happen. Both will end up using the same stack. So we are going to zero it out at that point. And then we restore the stack pointer, parent pointer, and the stack pointer to the right place. But now what happens is we additionally carry this value 2 over here, right? This is the return value of perform. So we print 2 here, right? And now our computation is back. It executes the rest of the function. So it prints 3. 3 is printed, but something interesting happens, right? Oh, what is happening here? So the mental model that you should have for delimited continuations is like, they are like functions. You resume a delimited continuation, it returns to the position where you resumed at. So we resumed from continue.
I call the function, I call that suspended function from continue. So at the point where I call it, the function returns. So we execute the rest of the computation, which is print 4, and we are done. And the point to notice here is that when this computation was done, we can immediately free this piece of stack. Just like how we when we return from a function, that space is free, right? So we can do that as well. So I painfully walk through how the runtime system works, but this is in fact how the implementation also works, right? You can build fun things with it. So the primary reason why we added this was for adding lightweight concurrency to the language. So I'm going to show you in about 20 lines of code how we implement a full-fledged scheduler in OCaml, right? So what we do is we start with the fx that you want to declare. I want two functions called fork and yield. Fork takes a function, right? It's a unit arrow. Unit is like a fallback that I'm going to run concurrently, right? And this unit just says that when you call fork, you don't get anything back. Yield just says I'm going to yield control, and you don't get anything back when you yield. It just comes back. So the main work happens in the run function, where you take your concurrent program and call main on it. I assume that there is just a queue of continuations here. I have not shown the code. It's a OCaml queue that just maintains a queue of continuations. The real magic happens here, right? When you call a spawn function on some particular computation f, the computation, what can a thread do, right? A thread can essentially run to completion, which is this case. When you run to completion, you just call the run next, which eventually call continue on the continuation that is already in the scheduler queue, right? You are done. You want to run the next person in the queue. But the computation can also do two other things, right? It can try to fork a new thread, or it can try to yield control. So those are just effects here, yield and the fork. The magic thing is we have the continuation here, right? The way to think about the continuation here is it's the handle to your current thread. So when I have the handle to my current thread, I can enqueue the current thread into the queue, and I call run next in the case of yield, right? If it is a fork, I handle the current continuation, sorry, enqueue the current continuation, which means it is suspended, and I recursively call fork spawn on this f that I want fork. So it has its own fiber, and it runs in its own fiber. So a little piece of thing, but in 20 lines of code, you can sort of write concurrent schedulers. And you can wrap this perform and fork and yield functions, right? So you can write a little program like this so that the user can write nice looking programs, right? So they can write a program that looks like, oh, my main function forks off two threads, tries to print two values with an yield in between. And when you run this program, you get the interleaved outputs from two threads, right? We've implemented concurrency, lightweight concurrency from scratch using these primitives. So that's what has happened. And the point is, the user code itself need not be aware of any of the use of effect handlers here. It's like you could have implemented this with pthreads also, right? The difference is sort of hidden underneath all of this, and that's the beauty of sort of building on top of this. There's no leaky abstraction like async await and function star for people who programmed in JavaScript. There is all of this things that you have to do, right? All of that is gone. You don't have to pay any cost there. Languages like Haskell and Go also give you this ability, but there the lightweight threads are implemented as primitives, right? So they are part of the runtime system. You can't change that. So here we used a queue in the previous slide. Oh, I have to go through this. We used a queue here. We could have just switched the queue to a stack, and you would get a LIFO scheduler, right? And LIFO is useful for certain kinds of algorithms that does breadth first search and so on. So there is a lot of flexibility to what you can do with all of this. And in fact, this is not just a toy, right? We built a full-fledged industrial strength concurrency library called EIO with this same idea. It has multiple backends, including IO Uring, which is a new asynchronous way to talk to the kernel from the user land. It's really wonderful. It sort of makes lots of things much nicer. And EIO is in production in lots of companies. This is based on the very scheduler that I have presented in the earlier slide. And I mean, we are fast, right? So the difference between garbage collected languages and non-garbage collected languages don't matter when you are
writing things like web servers, right, where all of your programs should be doing useful I/O. Yeah, it's back. So the graph here is throughput. It shows the throughput. So on the y-axis you have throughput offered. On the x-axis you have the throughput requests offered. And you can see that OCaml AIO is faster than Rust Hyper. Don't read too much into these numbers. You can make these graphs light, but it's in the good ballpark, right? You can make things go really fast. This need not be slow. That's the point that I want you to take. Okay, so now stepping back. So we've built all of this, and then we want to convince the maintainers to take our idea. So how do you do that? The other thing that we did is we built a wonderful benchmark suite. It's a rigorous, continuous, real-world benchmarking suite called Sandmark, where we take multiple compilers. Nightly, we run like thousands of programs, and we produce graphs where you can compare the performance of the multi-core compiler and then the vanilla compiler and see what the difference is. And we highlight changes which go beyond a few percentage points so that people are notified and they go and fix the issues. We also built something called OPAM Health Check. The idea here is very nice. So you take your universe of packages, you try to build it with both compilers, the existing one and your new feature. And the existing one is compiler 4 here, new feature is compiler 5. This was many, many months ago. And green here says that the package builds. Yellow here says that the package dependency does not build. And red here says that this package does not build. So because we were very much sort of built on this notion of backwards compatibility, most of these breakages were very small. We were able to proactively go and fix those features, made PRs to the package maintainers. They were able to merge it quickly. We got a good ecosystem coverage as well. Higher level point I want to make is, if you want to contribute to the compiler, you don't have to just work on the compiler code base. There's a lot of infrastructure that really needs your attention, and you can contribute to all of those. This is a very large scale distributed system, right? If you like distributed systems, you'd like building something like this. There are every commit that you make in the compiler triggers some 421 jobs that are parallelly built, right? So you need a very large cluster where you sort of figure out how to schedule this. Um, Very nice problems that are there in compiler development, not just writing the compiler code. Okay, I should finish soon. So I will try to finish soon. So I opened the multi-core OCaml PR in December 2021. It was merged in a month and a half. That's not true. I mean, we've been developing that for like 10 years, right? So the fact that it was merged quickly means that done all of the work for a long time. Even after merging, we needed a few more months of iteration to fix the design. It was finally released as a major release of OCaml called OCaml 5.0 in December 2022. And when these large features land, it's never that you're done, right? Oh, features landed, now I'm going to retire. There's always like a asymptotic curve for completion. There's always one nagging bug that is always need to be fixed. So we've been improving it over the minor releases. We still have performance bugs. We know where the bugs are. We just need to push them. There is like lots and lots of work to do here, right? I just want you to, this is not like a closed door. There is always like fun things to do in the compiler land. But there is also some exciting developments in the compiler. So one is called OxCaml, which is essentially we are trying to bridge the gap between OCaml and Rust, right? So Rust is great. I like Rust, but OCaml is also great. I like the garbage collector. Most of the times garbage collector is fine. So we are trying to bridge this last mile gap between OCaml and Rust using this idea called modes, which I won't have time to talk to. But we also have much better control of object layout, garbage collection, and so on. This project is led by Jane Street, but it draws lots of lessons from multi-core OCaml. So lots of papers. There is a CI already where you can see whether your package compiles with OxCaml or not. But it's different in other ways. So this experimental compiler is in production at Jane Street.
So there is a lot of valuable user feedback oriented design, which is very different from how multi-core OCaml was implemented. We did not have users. We had to predict how things go. Here, they can roll out a feature. If it doesn't work, they can roll it back. It's the wild west of compiler development. Um, but if all of this is interesting, you should get involved. There's a bunch of links here. You should have a look and talk to me. I'm going to be around for 2 days, so I'd be happy to talk to you. Thank you.
Thank you for a very, very important. I have a few questions.
Yeah, thanks for the great talk. So I'm a member of the Standard C++ committee and the author of the String Execution. So I was curious when you said that I have two questions actually. One is for the parallelization context, right? You mentioned that you have your slide has a comment that it's not thread safe for C++, but we have been working a large extent to make forward progress ensurement for true execution for all the algorithms that there is, bar and parsec, whatever it is. So I'm curious as to whether OCaml also takes inspiration from that implementation that we have for execution.
A really good question. Thanks for all of your hard work. I can't imagine working on C++ standards committee because the problems are much larger than what we have in OCaml land. So we did not take, to answer your question, we did not take inspiration. We took probably inspiration from Java, right? Where any RACI program will have to have semantics, right? It's not just like you sort of limit your programs to have semantics only when you use these things, use these additional primitives. Any program, even RACI programs, will have proper semantics, right? That's the difference.
Okay. And a follow-up question on that is regarding comprehensive. So you mentioned promises and other stuff, right? Features and promises. So we are introducing reflections in 26, which will probably come up in a couple of. So I think OCaml can also get upgraded with that for the C++ Postgres side.
Yeah, I'd love to talk. I don't know what reflections is, but I'd love to talk about offline. Yeah, so I'm happy to take
You got the questions.
one. Uh, offline, I'm happy to take questions.
Yeah. Yeah, my name is Jugendra. So my question is regarding, what do you see as OCaml's future on the non-CPU side of things, especially GPUs and other aspects?
So, really good question. So we have, I mean, the truth be said, we don't have a large ecosystem on the GPU side. We don't have any answers. So we are all binding to C libraries underneath for all of this. But there is an exciting project called Raven, which is trying to build the entire Python ecosystem for the GPU, right? Essentially, start from notebooks, PyTorch, low-level bindings, all of these, right? But it's a huge undertaking. There is some momentum behind it, but we do want to get there. But we understand that it's not a language problem; it's a community problem. If people want to hack on GPUs, come talk to me.
Yeah, thank you.
I'm Mitesh. I work on the JavaScript compiler at IT Bombay. So you mentioned that OCaml compiles to JavaScript. Do you think there is benefit to compile JavaScript to OCaml? And a follow-up question, you talked about implementing effects and the way they are implemented. So when we generate JavaScript code, finalizer blocks look very similar to the way they are implemented in our system. So when we were implementing it, we looked into the skins implementation of call CC because that can be used to sort of model all possible these cases. So was the inspiration also drawn from call CC when implementing these technical?
Okay, you had two questions. I'll answer the first one. I don't see how you can easily compile JavaScript to OCaml because OCaml has a stronger type system, right? In a way, we expect things to be statically typed. So I can write very simple JavaScript programs which will not have an equivalent OCaml program. For the second question, yes, it draws from lots of research on continuations, delimited continuations, call CC, all of these. Call CC is undelimited continuation. Here we do delimited continuations. Actually, they are much nicer, well behaved categorically. Um, so the inspiration for us is these operators called shift reset, control prompt. They are like sort of siblings of call CC. right? So we take a huge inspiration from all of that work.
Thank you, Casey. And happy to know that you're around for 2 more days.
Yeah, thank you very much for. Yeah, plug in the charger as well.
So we have 2 more talks in this session. The first one is NVIDIA framework for dynamic graph algorithms on GPUs by Kevin Broom from IIT Polytechnic. That is effective. You have 17 minutes time. You have to leave 3 minutes for questions. I'll show you 5 minutes after 12 minutes. So you have 5 minutes.
Uh, Thank you for having me. So, so my presentation today is about Mirkat. It's a library-based framework for dynamic graph algorithms on GPUs. So, point is not working.
The battery use with it.
Okay. Yeah. So, uh, so graphs as a data structure does not require an introduction to this audience, but graph algorithms are very challenging because the performance of graphs depends on the topology, and graphs suffer from irregular memory access patterns. Why I say irregular memory access patterns is because the degree keeps changing across vertices. Okay? So, for example, if you take a social network, you can have a small number of vertices having a large number of edges, but you can have a large number of vertices having a small number of vertices, right? So, for example, a famous celebrity on a social network might have a lot of followers, but common people like us may have a few hundred followers. So, real world graphs, they change in shape. New edges are added, some edges are deleted, sometimes new vertices are added, vertices may be deleted, just like how you see in social networks. So, when these graphs change, we require some very efficient parallel processing. Right? So the processing of dynamic graphs has not been explored well in the past in GPUs. So what we proposed was a library-based framework that implements some of the commonly used dynamic graph algorithms like DFS, SSSP, triangle counting, connected components. But in this talk, I would not be describing my framework as such. What I would be describing is what is known as warp cooperative work sharing execution model. Okay, and that is the fundamental thing which is powering my framework. Okay, so what is warp cooperative work sharing execution model? So on a thread,
Instead of assigning a vertex to be processed in a GPU, what I would do is each thread would have an independent task that is assigned to it. Okay, but all the threads in a war, they cooperate with each other using cooperative intrinsics to perform one independent task at a time, and that leads a very significant amount of performance. So, the warp cooperative work sharing execution model, although it's implemented in our library, we would like DSL compilers to take this forward to process some irregular workloads such as graphs. You can have other data structures like B trees and so on. So the advantage with using warp cooperative work sharing execution model is that it helps us to avoid control divergence and enhances memory coalescence. Now this is something which graph algorithms suffer on GPUs, and minimizing control divergence and enhancing coalesced memory access is something which is greatly desired in GPUs. Okay, so before I start explaining about what is warp cooperative work sharing execution model, I would like to brief you about some few terms that I would keep repeating throughout my presentation. Okay, so firstly start with what is known as a slab. A slab is a continuous block of 32 elements. Each element is of size 4 bytes. So totally a slab is about 128 bytes, and that matches with the L1 cache size of an NVIDIA GPU. So what you could do is that you could take the last element of that slab and use that as a pointer, okay? And you can chain these slabs together, form a linked list of slabs. This is what we call as a slab list. So when you want to do things like, for example, searching for an element, it may not be feasible for you to traverse through a single slab list. So what you could do is that you could distribute them across multiple slab lists, okay? And put a hashing function. So that hashing function will tell you in which slab list you need to look forward, and then you traverse through that slab list if you're searching for a given element. Okay, that is what is known as a slab hashing. Okay, it's a hash table that is composed of different slab lists. So you can take this idea and compose a dynamic graph data structure. Okay, so what you could do is that you can assign a slab hash, a hash table, to store the adjacencies for every vertex. Okay, so every vertex has an object, a hash table, which is stored on the GPU, which are storing the adjacent vertices of that particular vertex. Okay, so this is a framework in a nutshell. Okay, so in the bottom you have these allocators which are creating these slabs for us in the GPU memory, and on top of that we have hash table implementations. We have concurrent map and concurrent set. So the concurrent set is used for graphs for which you don't require to store the weight of the vertex, so the weight of the edge. A concurrent map is used when you have weighted edges in a graph. And you can use these hash table implementations to create what is known as a graph data structure called the slab graph. And on top of that, we have implemented a few dynamic graph algorithms. Now, these dynamic graph algorithms make use of cooperative work sharing execution model. Okay. Before I explain warp cooperative work sharing execution model, I would like to explain some warp level primitives which are fundamentally which are used as a fundamental basic block of this warp cooperative work sharing execution model. One of them is ballot sync. So in a warp, in a GPU warp, you have 32 threads. Each participating thread which invokes the ballot sync can pass a predicate. Okay, what ballot sync returns is a 32-bit value. Now, if a thread I passes predicate equal to 1, then the bit I in the return value will also be set to 1. If a thread passes a false value to the predicate, then bit I in the returned value of ballot sync will have 0 at the position I. Okay? That is ballot sync. Okay? So ballot sync tells ballot sync returns essentially a sequence of returns a 32-bit integer. It's a bit set which where the ith bit tells which thread has passed true value to the predicate. And you also have shuffle sync and shuffle down sync. So shuffle sync enables broadcast of a particular value to all the threads within the war. Okay, so if you, the thread which wants to broadcast will have to pass val as the second parameter, src underscore line is the thread ID within the war where the value will be broadcasted to the other threads. So shuffle down sync is used. So what happens with shuffle down sync is for a thread at lane L, shuffle down sync receives the value var from the lane L plus delta within the same war. So delta is the offset within the war. So the data is exchanged between the threads of the war. Okay, so you don't have to access the shared memory. So accessing the shared memory is a bit expensive because you might have to do a load, you might have to do store, you might have to do an address computation. So all of that is avoided. You can communicate within the warp threads with the help of warp level intrinsics. Okay, so now a warp has 32 threads. So in our framework, what we do is that we assign a vertex from the frontier to every thread within the warp. So in this particular example, the last two threads have not been assigned any vertices. T0, T1, T2, T3, and so on have a vertex that is assigned to it. Okay. So how do you maintain the warp queue? We maintain the warp queue by starting with ballot sync. Okay. So all the threads which have a thread to process will pass true value to the predicate which is required for ballot sync. So ballot sync will return a 32-bit integer. So the bit I of the returned value will be set to 1 if thread I within the war has some vertex to process. Okay. So then you elect the thread that has to be processed from the warp queue. So how do you do that? So you look at the 32-bit integer that has been returned by ballot sync. So look at the first bit that has been set by the 32-bit integer, right? So if for example, if in this case bit 0 is set to 1, so we have to process thread number 0, right? So now thread number 0 broadcasts its vertex, which is v0 in this case, to all the threads within the word. So you do that with the help of shuffle sync. Now once all the threads within the word have received what vertex to process, then you construct an iterator. Now the iterator is an object that will help us to walk through the adjacencies of the vertex v0. So the vertex v0's adjacencies in the global memory can be logically thought of as a single slab list here. Okay? So the iterator here now refers to the first slab. Okay? So you access the elements of the slab from the global memory into the registers of the threads. Okay. So now because the elements are stored in a contiguous fashion, you can do it in one single coalesced memory access, right? So what you fetch are the neighbors of the vertex v0, as well as a pointer to the next element of the slab. So s1 next that you see there is a pointer to the next element of the slab. So once you fetch the slab, you do some computation, right? It could be like a distance, it could be like a distance computation and so on. So once you have finished processing that slab, you increment the iterator which points to the next slab. You fetch the elements of that slab, perform the computation. Now you fetch the third slab. Now what has happened is, so you have reached the last slab here, right? So if you do plus plus iterator, you end up. So what you end up is having. So what you end up having is a pointer which does not refer to a valid slab, right? So that is an indication that you have processed the elements of v0. So now you mark v0 as processed, right? So now thread t0 will not participate in the election, right? So when you create the next warp queue with valid sync, right? Bit 0 will be set to 0 because the thread t0 is not participating. Bit 1 in that value returned by valid sync will be set to 1. So now the threads within the warp know that it has to process thread t1. Right?
You do the same process. You broadcast V1 in this case, construct the iterator, fetch the adjacencies of this fetch the adjacencies of V1, process the adjacencies, and keep on continuing until you hit the last slab. So you do this until you have processed all the vertices of the slab. So, uh, so, uh, this is in summary, right? So, so what you do here is you do an election here. So the election happens with balancing. Okay. So if warp dq or internally if ballot sync returns 0, then all the vertices within the slab have been processed. Okay. Now you find out the vertex which has been processed by all the vertices of the slab, all the threads of the slab. Then you construct the iterator, and you traverse through the adjacencies of the slab with the help of the iterator. Okay. So in fact, we have been able to we compared our framework with existing frameworks. Like for example, there's Hornet, there's a GPMA frame graph, and we obtain a significant amount of speed up compared to those frameworks. So for example, if you take Hornet, what Hornet does is that it distributes all the edges of a of the graph among all the threads. So each thread essentially receives the offset of the edges that it has to process. So it requires a sequence of edges to be processed. So although Hornet tries to reduce the amount of imbalance of the amount of work done by each thread, it does not avoid. I mean, it still suffers from uncoalesced memory access. So a frame graph, what it does is that it tries to distribute the vertices across multiple queues, but it still does vertex-centric processing, right? But our framework uses warp cooperative work sharing execution model. We avoid warp divergence, we have coalesced memory accesses, and we're able to obtain significant speedups. So so the source code is available on GitHub. It has been open sourced, and it outperforms existing frameworks. So you can get better performance if you use cooperative groups and make clever use of the L1 cache. Okay. So we have evaluated for different kinds of graphs. For example, power law graphs, random graphs, as well as road network graphs. Okay. Thank you. So I'm open to questions. So yeah.
Yeah, my name is Julian. So maybe a couple of questions. One is, how big is your graph?
So there could be like 4 million vertices and 250 million edges. One of the largest graphs.
Your graph doesn't fit in a GPU memory.
So we have not explored that. So in our test setup, we used a GPU with 11 GB of global memory. So we have only used for graphs which are fitting into that 11 GB.
Otherwise, you cannot.
Yes.
Okay. The second one is, have you looked at something like a graph neural net to see how it works?
Yes. So part of my research work is also on graph neural networks. I have not, so this is just on graphs where the edges have scalar values. Yeah. I'm also exploring on that direction.
Right for the book.
Like my presentation.
Yeah, thanks for the great presentation. So I have, so you mentioned that your framework avoids warp divergence.
Yeah.
And considering lower level PTX threads, that is, if you have logic predicates, it becomes a quite prominent use case for having warp divergence. So the static DFS example of the pseudocode that you showed us, how does it address that?
Uh, so uh, so so uh, so if you look at line number 12, the point. Yeah.
So what you do here is an election. So all the threads will receive the identity of the vertex that it has to process. So so then what happens is that you broadcast the thread. Sorry, you broadcast the vertex across all the threads. Okay, and then you fetch the adjacencies uh, of that particular vertex with the help of the slab iterator here. Now all the adjacencies of that vertex are stored in slabs, and these slabs are contiguous arrays of 32 elements. So in a single memory access, you get a slab. Okay, so if I do partition x rows 15 and then 16 to 31, that base is not taken into consideration. So if I split between the what essentially. Uh, so let's say 0 to 15 threads are doing some work, and 16 to 31 are doing some other work. Oh, for warp cooperative work sharing execution model to work. You are doing 0 to 32 exactly. Yeah, yeah.
So, thank you, Kevin.
Yes.
So we should move on to the next presentation. Take the questions now. Yes.
Okay.
Yeah. The next presentation is on me Pythonic DSL form. This all data. This button is for Python and this for the next and previous slide. Okay, this should just setting up a schedule form. Yeah. Like, you sure? Yeah. After 12 minutes, I'll say 5 more minutes. Okay. So total 17 minutes. Okay. I'll show 5 minutes. This is for print. This is the pointer, and this is for previous and next slide. Is it changing it? Good afternoon, everyone. I am Ishwar, final year BTech student from IIT Dharwad. I am here to present our work on creating a Pythonic DSL for radio access networks. I worked on this with my friends Rohit, Samath, Urjaypal, and our professor Nikhil Hegde and Makarand Kulkarni from Tejas Networks. So what is the motivation behind this? Radio access network software are targeted to be run on multiple platforms, and they have these models called as waveforms, which are developed in high-level abstract languages like Python or MATLAB. Then we spend huge amount of effort into rewriting them in performant languages like C for a given hardware. This leads to having to maintain multiple code bases for multiple hardware platforms. So obviously it will lead to more cost in terms of both time and money for maintaining all these code bases. And there is the issue of vendor lock-ins. And just hardware abstraction is not enough for this. If the just the ISA was the issue, we could have solved it using a hardware abstraction layer. But here, these heterogeneous multi-core platforms, even scheduling tasks suitably based on which task is suitable for which core, all those things matter. And on these platforms, setting up the I/O channels differ from one platform to another, and each hardware platform exposes a different level of parallelism to the programmer. So we need to have functional correctness between the generated uh, binary and the high level description of the waveform. And this is the one of the major challenges. So there is a need for a tool chain that can convert these Python or MATLAB definitions of a waveform to efficient target binaries. For this, we introduce PyDra. This is a Pythonic DSL for radio access network software.
we use MLIR as an intermediate representation. MLIR was built for solving issues similar to this in the AML world, where they have multiple hardwares like multiple GPUs of different architectures, and they had to we want to have a high level IR, uh, which is platform agnostic to capture all the operations of the RAN software, and then gradually lower it to the uh, target platform by adding more hardware specific details in each lowering. Um, for this, and we used the MLI dialects, standard dialects as much as possible, but we had to extend by creating our own dialects and passes for the following reasons. Uh, we had to implicitly detect parallelism based on the hardware profile. The compiler should detect implicit parallel loops and parallel regions without user inputs. Uh, and This is distributed memory parallelism, not shared memory parallelism like CPUs or GPUs, which share memory between the cores. And here, as I told, it's a heterogeneous multi-core platforms. So we have to decide which task is suitable for which core to perform. So we have to do the scheduling as well, and setting up IO channels and everything. And for digital signal processing, complex valued matrix and vectors are one of the important things that we have to provide support for. So moving on to the novelty and contributions, we decided to take Python 3.8 and compile emit MLIR from that. And we could have chosen ahead of time compilation or JIT. Many of you may know PyTorch, Triton, all those try to JIT compile Python, but we chose to do ahead of time compilation using Antler, so that we can get the AST closer to Python and not worry about um, going through the interpreter to get the bytecode, and then from there we have to get the AST. And auto parallelism in Python is kind of iffy because the multi-threading module is not truly parallel because of Python's global interpreter lock. Uh, you only one thread can hold control of over the interpreter at any time. We can sidestep this issue by using the multiprocessing module, but then again, it spins up new Python interpreters for each process, and that's a lot of overhead. And we decided to use OpenMP for expressing parallelism and offloading to the target. And they recently, like in OpenMP 4.0, they added the capability of offloading using OpenMP target construct. And in MLIR, it's functional within Flang. They are the major community which is working on OpenMP offloading. But it's not, there isn't an end-to-end pipeline similar to GPU. If you have used GPU dialect in MLIR, you can specify some code that needs to be run on the GPU, and then using some set of MLIR passes, you can get the GPU binary embedded in the host IR. There is nothing like that for OpenMP offloading as of right now. And for mapping descriptor based types to and from the device. For example, memrefs are one of example. They are modeled as a LLVM struct which has a pointer to the data that needs to be transferred. And one of the other challenges we faced were reports about the like when affine parallelize failed, the loop analysis of MLIR failed. If you have used poly or vectorizer, you can generate detailed reports on why poly decided that this loop or some part cannot be parallelized, saying there may be some pointer aliasing. But there is nothing like that for loop analysis in MLIR and this affine parallelize pass. So our methodology is, as I mentioned, we use the Antler parser generator. We give it the Python grammar to generate the AST, and then we can add listener methods to that, which get called while you're traversing the AST to emit MLIR. Um, we emit. We chose to we had the choice of using handcrafted IR or using the IR builder in MLIR. We chose to take a mixed approach because the IR builder, as you know, you have maintainability, you have readability, but it's difficult for beginners to get started with. And uh, as MLIR is constantly evolving with each LLVM version, there may be issues with non-compatibility. But the handcrafted IR is again not easily readable or maintainable, but it's easy to pick up. And we try to use as much MLIR infrastructure as possible because most of the some of the work are already similar to what is going on in the AML world. So we try to use affine analysis for detecting parallelizable loops, but it's just not enough to give R code and then say that affine will parallelize this. We have to bring in our domain specific knowledge here. We create a new dialect called RAN, which in a high level models all the operations used in the RAN software, which will obviously help us in the program analysis. And then one of the other things was adding support for maps. We model them using LLVM structs as like read-only LLVM structs. This is mostly used for data passing in the RAN software. And most of the NumPy operations we lowered down to BLAS or implemented our custom lowerings. And as I told, we are using OpenMP for offloading and parallelism. So here is the proposed like pipeline for OpenMP offloading, what it might look like. You have the input MLIR. Yeah, you have the input MLIR with the OpenMP target ops. You take that and then you run this mark declare target pass. This is similar to Flanks LLVM Flanks pass, where you mark all the functions called from within the target region, adding attributes saying this should be compiled for the target as well. Then you can have a pass which can take the module uh, which can create a new module for the target device, and then we can have another pass which says which gives more information about the target device, using which we can decide on more optimizations and parallelism. uh, so here is our workflow, how our uh, architecture workflow will look like. We have the Python grammar which we can give to Antler to generate the parser using the and you can give the our Pydra code to that, and we emit MLR in a very high level using our RAN dialect and other high level standard dialects in MLR, on which we can do the program analysis to detect parallel regions and parallel loops. We express them using the OpenMP dialect, as I mentioned, and then we can use these passes or OpenMP offloading passes I mentioned to get MLIR with MLR module for the host, containing all the code to be generated, compiled for the host, and one module for all the containing all the code for the target. And finally, we can lower all these dialects to LLVM dialect and the OpenMP dialect, uh, and to BLAS and other custom library calls. So we have these two modules. Then we can then from here on, it's just using the LLVM toolchain. We can get the LLVM IR. We first compile the target binary embedded in the host LLVM IR to get the host binary with the target binary embedded inside it. So moving on to the results, uh, we uh, we wrote the 4096.f50 program both in NumPy, and then converted it to MLR using our compiler, and then lowered it to the x86 platform. We observed 2 times speed up over the NumPy and Python implementation. But in C++, it was still like 5 times faster than ours. This is because we are very generous with our like memref operations, allocating new memrefs to capture whatever Python is trying to do as much as like with correctness. So if we have to work on this to optimize it more. Uh, we can definitely close the gap between our generated binary and C++. So some of the related works in this field are one of them is the DSP MLIR, which tries to model all the digital signal processing microkernels in software and then optimize on them. And then the other one is on FFT code generation using MLIR, lineage dialect, and some SIMD microkernels. And obviously, Triton, NumPy, and PyTorch, which all try to do something similar by just compiling Python to some hardware, like target hardware, GPUs mainly. And there is this project called Torch MLIR, which takes the Torch Dynamo output from PyTorch 2.2 and then converts it into MLIR. So in conclusion, hardware is shifting from generic to application specific for having more like to extract more performance. And based on the application, the PPA metrics vary. Uh, and this rise in multi-core heterogeneous hardwares leads to more programming complexity for the programmer. And it's not just limited to the ISA, which is different, but also all the data flow and how the data is managed on the target hardware. So identifying all these on the SOCs and then having a work with the workload distribution, optimal workload distribution is crucial. So this also this our project gives separation of concern. The programmer doesn't have to worry about the underlying hardware. He can just think about developing the model, and our compiler can take care of the target, uh, compiling to the target efficiently. This is what this is the same thing in the AML world that MLR is trying to solve, and this is adaptable to the RAN software world too. And this hardware software desegregation will lead to the open RAN ecosystem where the programmer can worry about just creating the model and not the target hardware. Yeah. Any questions?
Hi, I'm Arjun. Thanks for the talk. So I had a question on the results. You benchmarked it in x86 system, right?
Yeah.
Is that also the target hardware for your compiler? I thought it was more like an.
Yeah, this one was on x86, but our goal is to offload to other like digital signal processors. But this result is from x86.
So there are actually two sub questions. The first would be, are there, if you were to use another standard like a linear algebra type compiler in MLIR, without using your target, would that be faster than what you have? Because it seems like for x86 that would be optimal.
Yeah, for x86, there are many existing implementations. So,
So with that, would you be able to get close to C++ with a 58W2 or?
uh, yeah, but this result was just for as an experiment on x86. So it will be moved to some digital signal processor, right? So we need to have support for the 50 on that board.
And yeah, the other question was, so is this understanding correct? So when you talk about a request,
Yeah.
or radio again, so you've got a bunch of such DSP cores.
Yeah.
So the scheduling problem there will be different from going trying to
Yeah, yeah, obviously here it's not heterogeneous and everything. This was like a first level for us. If we can schedule it on the CPU, then we can look into scheduling it on the target hardware, right?
Okay. Thank you.
Thanks for the talk. You said that you could get more improvement in your performance, or other your performance is kind of limited because of your memory allocation, like because of
Yeah.
how Python works. So, what would it take to close that performance gap? And
We will have to uh, obviously do all the analysis and see maybe where we can cut down on the allocations. After we get from Python to MLIR, maybe we can try to minimize some of the like redundant allocations based on how Python works, right? Because of Python, we will have some redundant allocations. If we can figure that out, like in a pass, then we can remove all those operations. We Yeah, we can continue this with like offline with our professors too.
thank you very much. Sure. Thanks.
That brings this session to a close. Snacks are served on the right. Tea will be here in another 5 minutes, maybe. And the food as a would be from the and we'll meet again at 4 p.m. sharp in the next session.
Which means before we go out and stroll in this beautiful campus and the beautiful weather, you have the last opportunity to stay alert and learn more about the virus. So I have four interesting talks in this session, ranging from high-level language specifications and distributed systems, GPUs, and new-level thinking. Very exciting session with the variety. Our first speaker is Vaibhashwat Nagaraj. We will be talking about the declarative IR specification in a tool called DLM. Feedback. Today is on declarative IR specification in Iran. We talk with a brief introduction to what Iran is, and then I talk about the problem that we try to solve in that year. This is how MLIR solves the similar problem, and then talk about our solution in more detail. So, there's an extensible compiler IR infrastructure that's built completely in Rust and shares the same goals as NVIDIA. Presented here at ILCT last year. Extensible compiler, engineer can easily define new operations, types, and other IR attributes, and then use the infrastructure now accommodates all of these new definitions into writing analysis and transformations. And these new definitions can also be grouped into what we call intents. What we're on it, and then explain the problem that we're trying to solve. I have here an example of the loop that I'm trying to define with Iran. It's a constant call, which means that it always defines a single constant value.
where there's verbose code, boilerplate code, and all of that, and we want to avoid writing all of this manually and somehow automate generating it. MLIR, being an extensible compiler itself, also has a similar problem. So let's just first try to understand how MLIR solves this problem. MLIR has operation definition specification, or ODS, that is part of its table chain. Table chain was originally written to be a part of LLVMs for specifying target descriptions, but it has now been extended to perform a lot of other things, including specifying the IR and MLIR. I have here an example of the definition of an extract element op. This is from MLIR's LLVM dialect. And it's quite straightforward. First, there's the op name, and then you have some documentation. Then you specify arguments, result types, and other attributes that are to be part of the op. And then you can see that there's a nice syntax declaration here. This is kind of what you also want to have. You don't want to write a printer and a parser manually, but just based on this kind of a syntax, the tool should automatically generate a printer and parser. And finally, there's some embedded C++ here for custom inputs. So, when we realized that we want a similar declarative system for declaring IR entities later on, our first thought was, of course, to have a tool, something like TableGen, to also have it for Iran. But then we realized that Rust has what are called procedural macros that are quite a powerful feature, and they can instead, that you can use that instead. You can use that instead of having a separate code. So let's try to understand how Rust macros work before I get into the details of how that works. Here I have an example of a trait called 2 bytes. As I mentioned before, a trait in Rust is like interfaces in Java, abstract classes in C++. The 2 bytes trait here has a single method called 2_bytes. The idea behind this trait is that any type that implements this trait takes itself as argument, and it's equal to a vector of bytes. And what I'm doing here is, you can see that this here is a macro annotation. And when I annotate the struct foo here with the derived 2 bytes macro, during compilation, when the compiler compiles this and expands the macro, this is the code that gets generated. And this code is quite straightforward. All it does is it calls the 2 bytes method on each field member of the struct, and then just concatenates it. Now, what is interesting for us here, as in the context of this talk, is that how do we define this macro so that it can generate code automatically like this? The definition of the macro itself
what I'm doing here is referring to the it looks like something like 42.7 that we have. And the third example, we have in the second case, I have a vector of a list of some values. And in the case of specifying that something is a list or vet, there's also a separator character that needs to be specified. And once I specify the string, a printer and a parser that can print and parse this kind of a string for the struct is automatically generated. There's nothing more that you need to do. Rust enums also work pretty similarly to Rust structs that we saw. You can just say hash format on enum and be done. There's a default syntax that's automatically generated for you. If you want, you can also customize one or more of the variants of that enum. And in this case, I have customized some of these variants. The syntax string again is quite similar to what we saw before. There's nothing much to explain there. But you can customize variants of an enum also. Okay, so far we saw how you can generate printers and parsers just for Rust types and enums. What about IR entities that are part of the actual IR infrastructure and thereon? So types and attributes are, well, they're fundamentally just Rust struct and enums, and their semantics are based on that. So there's nothing more to do. It's as simple as just saying hash format or customization that we saw so far. Ops, on the other hand, are a little bit different. This is because ops are essentially thin wrappers around common container data structure. That's the operation that contains operands, result types, attributes, and all of that. But again, like before, we can just have a canonical syntax for an op as well. We just need to say hash format op, and that's it. There's a canonical syntax generated for the op. You can as well, like before, customize how an op is printed using a custom syntax string. We'll see examples of this customization in the next slide. The first example that I have here is copy op. All it does here is just copy the operand into the result. And to specify the syntax, we say $0, $0 here means the first operand. And then we print the type of the first result. And when this is printed, it looks something like this. This is kind of a functional syntax where we say, colon and then the type at the end. And similarly, for the constant op that we saw earlier, as I said, a constant op always just defines a single constant value. And since this constant value is stored as an attribute in the operation data structure, all we have to say, all we have to do is mention the attribute name, and that's it. The attribute name is now part of the formatting. And when this op is printed, it looks something like this. The op name result is equal to op name, and then the attribute is printed. In the third example, I have this is an if-else op. It has two regions, so I'm using a region directive. The argument to the region directive is which region do you want to print and at what place. And all this is saying is that first print the condition and then print the then region and then the else region. And when printed, it looks something like this. There are plenty of other directives that are part of the format of macro, and there are many more rules as well. All of them are documented as part of the op. There are plenty of examples as well, so that you can refer to them to define new IR entities. So far I spoke about defining an op and defining the syntax for an op or other IR entities. I have just a few more examples here. This is the global op from Pliron's LLVM dialect. And what I'm doing here is, first there's the def op. This is to just say that this is actually an op. And then I'm automatically and then what I'm doing is automatically deriving some op interfaces for it, and this is the derived op interface implementation. This is yet another macro, and with just this, these interfaces are automatically derived.
And then there's this attribute, there's this macro to automatically derive some getter and setter methods for attributes on the op. You can as well specify what the type of those attributes are. And the nice thing about this macro-based approach is that, you know, there's a nice documentation that also automatically gets generated just based on this declarator spec. So here, you know, for the global object we saw before, these are the attributes and what are its types. All of that, you know, it gets into a nice looking table. This documentation, all of this is automatically generated. Yeah, I'm almost done. So I just want to end with trying to compare how these two approaches, you know, one is MLIR stable gen and the other is the macro-based approach. How do these two compare? Firstly, both of them share the same goal. That is, you want to be able to declaratively specify your IR rather than procedurally. What differs is just the languages. You know, either the language of specification or the language in which the tool or the expansion function is written, and what's the target or the generated language. It's just those things that differ and nothing more. But having said that, the table gen tool itself is a far more versatile tool in the sense that it can do a lot more things than just define IR entities. And also the language itself, the DSL that's part of table gen, it's quite more powerful in the sense it has templates, class hierarchies, and so on. And what next for us? Well, at least immediately what we want to have is some way of expressing constraints and logical operations over that. You know, for example, you should be able to say this operation has exactly 2 operands or exactly 4 operands, something like that. And finally, well, I've spoken about all of these macros, you know, that have been helpful to us, but it would be nice if we can unify them all into one single macro. Equal in what it can do. You know, it can express the same things, but this looks neat. It's easy to read and it's easy to maintain. So we want to have this also in the near future. So that's it. I'm done. Thank you.
Thanks, Devashwat, for a very interesting kind of work. We have questions.
Thanks for the wonderful talk. The question I had was, in TableGen, you have a separation of concern, right? You have TableGen file that declares the op, and you have C++ files where you have the implementation. So the thing is, when you update a TableGen file, only the TableGen files are updated and the completion happens. Whereas in Rust, when you update the non-op portion of it, would that be another recompilation of regeneration of those?
Yes, so well, this is a backup slide, so just look at the second part. So the separation of concerns that you said, right, in my opinion, actually a disadvantage. And the reason I say that is, let's say you're opening your project in an IDE. There's actually a disconnect between the C++ code and the table gen code. If you, for example, let's say you're using an op in C++ and you click on it, you know, go to definition, it doesn't take you to the table gen definition. It takes you to the generated C++ code. So there's a disconnect. And similarly, if you're looking at the table gen code and you immediately want to see, you know, what's my generated code for this, you have to search around for it. Again, there's a disconnect. But that doesn't actually happen here. What happens here is, so the macro annotation is right in the place where you actually define your op. So when you say go to definition for this op, it takes you directly to that one single place where everything is. And to directly answer your question, if you want to see what's the expanded version, in an IDE, for example, you can just click on that.
No, I should.
Yeah, right. Yeah, I think this is interesting. So my question is mostly on interoperability. So for example, now we use this framework to write once like new dialects or maybe a new dialect.
then want to use Rust as a compiler. So define this using this, but then next I want to write transforms or classes that use this dialect in conjunction with the existing MLIR C++ infrastructure, the existing. So I don't want to redo the whole. I think there's some standard dialects and operations that are there. So how do you interrogate write classes that will in Rust and using this framework? My dialect defined here, and with other things coming from the existing MLIR that probably won't work. So that actually gives slide of the code. At some point we did consider just using cable connect. The main problem is a lot of decorations and cable connect that's there in Himalaya. We have a lot of embedded C++ code. So this is solution that can do all other than C++ Rust.
Yeah. But I don't see any other way of doing an interop quite easily. But maybe something with a language agnostic to like IRDL or something like that. Then we should be able to have some kind of interop, I think.
Okay, because then you would have to duplicate the whole infrastructure, right? All the data.
Yes, yes.
And if there is some automatic way to create that in this universe, and then also it's not just the direction of, but we have parsers and other libraries, transforms analysis. So
That is a
discussion offline.
That is a downside.
It's a very interesting area to think of. Okay, thank you. Next time, Vishwanath again. The next speaker is Rupashri Rangayankar, who will be talking about support for orthogonally replicated data types in context of distributed consistency.
So this button right here, the red one, so the pointer, this is for the next slide, this is for the previous slide. Okay. So, nice. The one you got, up.
I want to present a view. Yeah.
Solution. Can we test the demo?
I can see still.
How far you are? What can check out? I should have on the slides.
Can I test?
No, it's not. I'm not on the slides. Not on the slides, team.
Not sure.
Okay.
Hey, now I need the presenter view. Presenter view is where you can view it there, right? I can't see under that place. You can't see? Yeah, that's right. Alright, yeah. So, but let's hope that can you see when you are here, it's working. Just change it on. Yeah. Hi everyone. My name is Rupashri Rangayangar and I'll be speaking about compiling distributed consistency. This is basically initial thoughts on designing the compiler for orthogonally replicated data types. I'm going to structure my talk into two parts. The first part is actually going to speak about a language called Gambit that we are building at Princeton and the support for compilers necessary for it. And this is joint work with Dr. May Milano at Princeton. We are entering a new era of distributed programming centered around programs which communicate via loosely synchronized
replicated data types. So in this dynamic language that we are building, the primary or the first class citizen data types are orthogonally replicated data types. So what are RDTs? A replicated data type can be thought of as having six components: a state space that represents what each replica stores, an initial state function that sets up each replica, a message set for inter-replica communication, a do function that executes client operations locally, and a send function that generates messages to broadcast changes, and a receive function that merges incoming updates from other replicas. In the last few years, a whole alphabet soup of replicated data types like ARDTs, MRDTs, CRDTs, PRDTs, just to name a few, have arisen, each with a slightly different story on the expressiveness of mutations permitted, the ease of extending each data type, or the process of proving convergence properties. These data types have in turn powered a quiet revolution in cloud development, enabling everything from strong privacy to ownership protection of the local first movement to the extreme scaling and performance of the ANA and the Hydro database systems. If you see this picture, the distributed shopping carts problem, which was made popular by Amazon's Dynamo, this is an essential business problem with a clever coordination-free solution. So consider the leftmost scenario. A user that wants to add items to the shopping cart could send his request to different replicas. When the ad goes to a replica, it gets added to the cart, whereas a remove could essentially be a no op. And in this case, when you try to merge, you would end up with the item still in the cart. So this is unclear if it matches the user's expectations. Solution to this was CRDTs, which are conflict-free replicated data types that allow independent concurrent updates without coordination, and they automatically allow conflict resolution through mathematical approaches like um, um, commutativity, associativity, and idempotency. Whereas CRDTs had a programmability problem. To define a new CRDT, you had to come up with an entire paper worth of contributions. So MRDTs came into the picture, which basically defined data types in a format that was mergeable. And they solved the programmability problems of the CRDTs. Despite all of this, we are still left with data types that do not know how to safely observe state, and we also do not know how to safely perform non-monotonic operations on these data types. Ergo, ORDTs. So these are new programming abstractions, and as you look at that abstraction, we also have a state space, and we have operations which are essentially mutations, observations, and merges. But the addition to this is actually active restriction. That is a mechanism where we can limit the natural interface of the data type through three aspects. We limit mutations to ensure that it is commutative. We define conflict resolution semantics, and we limit observations to maintain sequential consistency. And additionally, whenever an operation is blocked because of restrictions, we issue contingencies to notify the user that the operation did not go through. So the whole reason why we call this orthogonally replicated data types is that we separate what to replicate, how conflicts are resolved, and which consistency model to provide. So again, as you can very clearly see, these ORDTs are again replicated data types. Like CRDTs and MRDTs, the replication occurs asynchronously. Mutations and observations do not wait for synchronization to occur, and individual replicas may definitely get out of sync. And we call this property weak replication. ORDT's weak replication has a very important availability property. Because of this property, the ORDTs can remain available for a certain class of mutations and observations even during partitions. And the latency of the observers and mutators at a single replica will not generally depend on the performance or availability of other replicas. So, moving on, if you have other questions about the restriction system, we can definitely collect offline. So, like existing literature, we also define the answer to the question, how does the state evolve across distributed replicas through lattice theory?
So, unlike CRDTs, which focus on operation level semantics, ORDTs structure the entire state space as a complete lattice where the merge function itself is monotonic. So, the state component is a product lattice which has an inflationary lattice component and a non-inflationary lattice component, which basically orders removals in an inverted lattice and reframes them as additions to an inverted lattice component. So we provide a library suite of data types wherein we take a raw data type, lift it into a format called the characteristic relation that is promoted by the MRDTs, and then we define our merges atop it as well as our operations atop it. So we lift the mutations, we lift the observations, we lift the merge function itself, and then we define new data types. And this is our suite of library data types provided in Gambit. So the critical question here is that we have a n-way merge function. So essentially, a three-way merge requires O of n sequential merges where intermediate states might violate the restrictions that we specify, which are business constraints or invariants on the data type. So in order to handle that situation as well as perform safe non-monotonic operations, we define an n-way merge function and the formula is given. But the correctness of such an n-way merge function should still follow all the mathematical properties of commutativity, which is essentially that there is indifference to the ordering of messages, associativity, that arbitrary batching of messages should be allowed, idempotency, that is, if you apply the same message over and over again, you get the same results. The preservation property, where all the allowed operations per a restriction should be preserved. Restriction compliance, that is, all operations that are blocked by restrictions should not appear in the final state, and then essentially convergence. That is, no matter how you permutate the order of operations, your replicas should converge to the same state. There is traditional definitions for sequential consistency, which is basically Lamport sequential consistency, which requires processors to issue memory requests in program order and memory modules to service such requests via FIFO queues so that you create a partial ordering allows any total order respecting these constraints, thereby achieving sequential consistency. Well, that does not work for ORDTs because when you consider the execution of a concurrent ORDT based program as a set of traces of mutations and observations against ORDTs with one trace per program thread, we will have to think about this as that there must exist some sound single sequential trace made up of these exact same observations and mutations. In other words, for every observation we make in the concurrent execution, there must be some equivalent observation that we could have made in the sequential observation, and it must have yielded the same observed values. As we will see, carefully controlling both observations and mutations that may be performed on an ORDT is key to maintaining this guarantee. So, what we actually need is sequential consistency modulo observations. So, a distributed execution is sequentially consistent modulo observations if there is a global linearization of all operations that preserve all replica local ordering as well as preserve the read consistency. That is, we do not care about the precise state of each step, but only that observations return the same results they would in some sequential execution. So this lets us reason about distributed systems where non-determinism and reordering are okay as long as observations look consistent. So let me take a pause here. That was a lot of domain knowledge. But what did we understand? Summarizing, we have a replicated data type which is present across different machines. Each of these replicated data types have state. They have operations on them, which can be reads or writes. They have to converge to a particular value. And somehow this convergence should maintain sequential consistency. And this is where we need the compiler because we want to verify a lot of these properties at compile time. So think our Gambit programs typically look like this, where you write the domain knowledge, you encode the restrictions, you specify the ORDT that you have,
and then you say the kind of mutations and observations that you do, and then you forget about everything else. A large number of existing distributed programs can be just written with a max of 35 lines of code. And that is because, unlike CRDTs, where each new data type require custom proofs, ORDTs can be designed to provide a universal framework where merge functions can be automatically derived. So we want to make the programmers focus only on domain logic rather than distributed systems complexity while still giving them very strong sequential consistency guarantees. So, how is distributed consistency being verified today? A developer writes code, they deploy it to production, network partitions occur, inconsistent states emerge, the system fails, the developer debugs and fixes it and redeploys, and this is done ad nauseum. Whereas in ORDTs, we want to verify restriction compliance, merge function correctness, and consistency at compile time. So this is essentially our compiler pipeline that we are writing for the new DSL gambit that we have designed. The goal of the compiler pipeline is to transform high-level distributed programming into provably consistent distributed systems. So the programs are written in Gambit DSL, which is the domain-specific knowledge, and then they specify the domain restriction mutations and observations. The DSL is parsed and lowered into a custom MLIR ORDT dialect where we synthesize the merge function. The compiler's core innovation that we have is a comprehensive verification pass, and this is powered by Lee, which ensures correctness by statically checking restriction compliance and provides the merge function properties such as commutativity, associativity, and idempotence. And eventually, we also test for sequential consistency. This verified IR is then lowered into LLVM IR, leveraging standard compiler optimizations while preserving the verified semantics. Finally, the code gen that we produce is a set of native replica binaries, each with embedded configuration for a particular cloud target, which can be directly deployed. So this pipeline that we are trying to design ensures that distributed programs are not only efficiently compiled, but also mathematically guaranteed to satisfy the correctness properties before deployment. So our ORDT dialect is very standard. We have defined library data types. We also have certain operations, and we define the attributes as well. And in the interest of time, I'll just quickly move on. So we have several MLIR snippets that we have generated for each one of these distributed programs. Finally, our goal and the work in progress that we have and the core innovation is multi-layered verification. So we have a three-tier verification strategy. The first layer is just the static analysis that we do at MLIR, which just performs basic type checking to ensure that all the merge, add, and remove operations have the proper operands and the result types that match the dialects type system. So MLIR also, we automatically verify through tables and operations, and uh, and using the C++ verify methods. So the second step that we do is structural restriction compliance. So we statically prevent invalid operations like adding or removing when we have specified a restriction on an ORDT to be a read-only data type. So we store this restrictions as type attributes, and then the verifier can reject this at compile time. So basically, at the layer 1 stage, we ensure that programs are well formed. The layer 2, we ensure that we have lean certified functions, which is basically semantic verification. So every ORDT merge operation is hardwired into a lean provided definition, and we use a certificate registry system with structures like lean certificates which contain theorem names, the property types, the verification status, and proof strategies. So whenever MLIR lowers a merge operation, it checks the registry to ensure there's a certificate with verified status. And if no such certificate exists, pipeline fails and we cannot generate code depends on an uncertified merge. So this layer, we try to build programs that are correct by construction. At level 3, we try to prove sequential consistency. So we try to prove this as a global property where every possible distributed trace of operations has an equivalent sequential interleaving.
So in the third stage, what we are focused on is that programs are well behaved under all possible executions. So this is again the innovation that we have where we try to prove merge function is provably correct. In ORDT dialect, merge operations are just placeholders and they don't have the entire merge logic. For each restriction policy, we have lean definition with proofs and when MLIR operations are lowered, the compiler just pattern matches on the restriction type and directly invokes the lean certified function. And then it directly generates this LLVM call. So the critical constraint that we have is that only proven proofs are exposed. So essentially what we fall back on is that we make sure that the lean compiler generates the C code and then implements those proven merge functions. And then we just use that data in our lowered LLVM as a foreign function interface or an FFI or an external call. So I'll stop here. You can speak to me about anything that you want related to Gambit, ORDTs, and compiling distributed consistency.
Thank you for the data. So I have a question regarding the theory-based constraints that you apply on your expression. So you are saying commutativity and distributivity, but not all systems are saying saturating integers. So these sort of are different kind of EM formats, right? Which do not maintain this kind of rules in MATLAB or something like that. So how do we preserve? How do we write the theorems in that case so that it solves your timing and then
As I said, we have a very limited set of data types, all of which are complete lattices by construction. So we identify the fact that merge is not available on every raw data type that is existing in the universe. So what we do is we lift that raw data type into a set representation because we know that sets can be merged. And this idea is predominantly coming to us from MRDTs, but we have a stronger criteria for abstraction and concretization. So as long as you can write whatever data type that you have as an isomorphic data type to one of our library data types, then you're guaranteed to have the consistency guarantees that we specify in LEAP. Did I answer your question?
yeah, yeah. That answers. I have a one follow-up question.
Yes.
So let's say for complex kernels, right, we transfers from different kinds of memories depending upon what accelerators or things we have. So how do we ensure that the sequential model that is happening on let's say localized memory is also happening in the same way when often we do a sophisticated accelerator? Let's say, for example, local share itself.
So here, if you formalize sequential consistency, it's not sequential consistency as high-level processes that Lamport or any other Hurley's definitions mentioned. So the way that we have formalized sequential consistency itself is on the operations. So any program that you execute in a distributed environment has a series of reads and writes that happen to that data type. So we say that if you have that order wherein every instruction follows the program order on every replica. And then when you merge them, it follows some sort of an observation consistency. So we define consistency from the perspective of the user. So a client on how they observe. When we say if that is a total order, or you can put it in some sort of a total order, as the observer would have seen, then we say that your program is sequentially consistent modular observations. So I'm not sure if I answered, but we can speak more. Yeah.
Thank you. Let's take more questions offline. But thanks, Shruti, for making a complex topic very accessible.
Thank you. Thanks.
Speaker is Tommy Kumar Basu. We'll be talking about
Audio check one, audio check one. Hello, 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 hello. Better, better, better. Better. Only to do it. That's fine. Yeah, that's fine. Uh, it's fine. She's just. This should be. Okay. Thank you. Hello, everyone. I am Shomit Kumar Bosku from IIT Hyderabad. Today, I'm going to talk about global synchronization optimization for heterogeneous computing. It's not, it's not, it's not working. Wait, then I have no, didn't do it. I think this is called. I think this is called. Nice one. Yeah. So let's start. So the content here I am covering is first I will cover the overview of the GPU architectures and programming, then the problem I am actually addressing, which we call heterosync motion. Why you will get to know. Then our approach, GSOC, then followed by the results and conclusion, and some of the future works also. So the first thing is the execution of a typical CPU GPU heterogeneous program. You have a CPU which have multiple cores. The CPU has its own CPU DRAM, and the GPU has also similar to the CPU has many cores and also has a GPU DRAM. Both the CPU and the GPU DRAMs are connected via a PCIe Express bus. Now, okay, the slides are actually not properly coming. Just, now, sorry for that. Oh, yes. Yes. No, it's not. Oh, yeah. Yes. Okay, thank you. Thank you. Now it's now it stopped working. I can use this also. That's fine. Correct. Okay. So let's see a typical execution of the CUDA programs. Here for just examples, we are just working on the NVIDIA CUDA programs. You can have the similar kind of taste over multiple like other CPU GPU programs such as OpenCL and all. So here, if you see that you have a CPU function, and here at kernel 2, this kernel 2 is a GPU kernel which is which is executed on the GPU on multiple cores. Then you have the CUDA mem copy call, which is actually responsible for the data transfer between the CPU and the GPU. Next, you have a CUDA device synchronize call. The CUDA device synchronize, you have a synchronization call which stops the CPU execution until all the previous GPU computations has been done. Surprisingly, the CUDA mem copy, which is a data transfer operation, is also a synchronous call, which means it stops the CPU computation until all the previous GPU computations are done.
Now at line 9 and line 18, you have some CPU computations. The dots represent some CPU computations, which actually is not dependent on the kernel too. However, though it is not dependent on kernel 2, you can see these two calls, CUDA copy and CUDA device synchronized calls, are restricting the CPU and GPU computation to be overlapped with each other. Here is a block diagram for that. The synchronous call is actually making the host computation or the CPU computation wait until the device computation is finished. So, how can we improve such a ill-written program? The solution is pretty simple, that you just percolate the synchronization call after this independent host side computation, and you get the host side computation and device side computation overlap, and you get the performance boost. However, this solution has several challenges. But before the challenges, here are some of the great motivations we have found in the GitHub open source projects, where we have shown that in our paper also, that programmers actually do such kind of mistakes. On our on my right hand side, we have the graph coloring problems taken from the score benchmark suite. We have the assign colors kernel, and there is this detect conflicts kernel, which is actually understanding the conflict between the different nodes in the graph. If you can see, this divide work computation is trying to divide nodes or assigning the nodes to different threads in the GPU, which is actually independent of the assign colors kernel. However, they still cannot be overlapped because of this CUDA copy and CUDA device synchronization calls. Now, so coming back to the challenges, you have seen the problem, you have seen the open source real world problems. Let's come back to the challenges. For this CUDA copy call, where to percolate this? The challenge one is the need to check for the data dependency, because the CUDA copy calls are the data transfer operators. You cannot place them randomly anywhere. See here that the CUDA copy is writing to array v, and at line 20 inside function foo, the x is being written, which is nothing but the array v. So you cannot place CUDA copy after line number 2, line number 20. That's final. Challenge 2 is that simply checking for the data dependency will not help, because if you place inside the if condition but before the line 20, then the data transfer is conditional on the predicate at line number 19, which may or may not happen. But in the original code, the data transfer was guaranteed to happen. Challenge 3 is that while percussion, you need to consider the farthest target location possible while maintaining the dependency. The last challenge, a program may have multiple memcopy statements or multiple synchronization statements, and it is very much cumbersome or maybe also error prone to actually percolate all the memcopy statements at once. So we provide an automatic approach for this, which is called GSOC. This is the whole pipeline for GSOC. We have two phases, static analysis phase followed by an automatic transformation phase. The first step of the static analysis is finding the target locations, then updating targets, then unifying the targets. Lastly, it finishes off with the automatic transformation phase, which we call the heterosync motion transformation. Let's come to the step 1 of the static analysis phase. Here I am using the interprocedural control flow graph of the same program, or the same example program that I have shown. It actually finds out the target locations based on the data dependency. How? It starts from the start node of the main function. It comes here and it finds out that, okay, this is a CUDA copy call, but there is no target location assigned to it. So it finds out that at L10, there is a foo function call. It starts analyzing the foo function. At L20, it finds out that the X is being written, which is nothing but the V was being written in the CUDA copy. Data dependency found, and okay, we have now a target location for the L5 or the CUDA copy call. And after that, it comes back to the foo function. At here again, it finds another dependency that at L13, the V is again being written. Now, the L5 has two target locations, L20 and L13. It comes back to the end. That's fine. Now we have two target locations, but the problem here I have already told that it cannot percolate inside the if conditions. And if you see, both of them are actually inside a conditionals. So how to deal with that? The data transfer here depends on the predicate that we all agree with. So this is handled by the next step, which is called the updating targets. Take these source and target pair, L5 and L20. It actually goes to the predecessors from the target locations and tries to satisfy that the dominance and post-dominance relationship between the source and target locations. Here, it actually satisfies the dominance and post-dominance, and we update the target map. Next is takes this L5 and L13 pair, it goes above, and here it also satisfies the dominance and post-dominance relationship. But here's the problem. It is a loop header. If you place the CUDA copy inside, like, or at this point, it will iterate over multiple iterations, which actually like brings the whole program performance down. So you have to go to its predecessor also. Here it satisfies and it is not a loop header, so the target map is updated to L11. For now, we have the updated target maps of L19 and L11. But one thing that how do we actually satisfy the condition of the dominance and post-dominance across function boundaries? We actually use the interprocedural dominance and post-dominance by the means of transitivity, and we also leverage the transitivity properties of the dominance and post-dominance relations. We introduce the notions that which is exit dominance, common dominance, and entry dominance. For the time being, I'm not actually saying what are individually those, but I will be happy to take questions on those, which actually, if you see, it forms the dominance and post-dominance path from the source to target. Now, coming back to the step three's motivation, we have now two target locations, but the problem is we cannot percolate the single CUDA copy to two of those target locations. It will cause multiple data transfers. And as you know that in these heterogeneous programmings, the data transfer actually are a bottleneck. We do not want to increase the number of them. So what to do? That is done by our step three. We actually only keep the target location which dominates all the other target locations. For example, here L19 dominates the L11. So instead of keeping L19 and L11 both, we only keep L19 as the final target location. Finally, after we have one-to-one correspondence between the source and target, we move on to the automatic transformation phase. And here we simply percolate from L5 to L90. But again, this is not also very simple because we need to change the function definitions and as well as the function calling context. From the calling context, one thing to be noted that if the function is called from multiple contexts, we do not percolate the CUDA copies inside the function body, but rather we keep at the function calling context itself. Now, coming to the evaluation, we have tested on three different platforms, which contains three different GPUs, and we have found 361 opportunities in 56 different benchmark programs. Around 48% of the benchmark programs have interprocedural opportunities, the benchmark lines of code ranges from few hundreds to around 18,000s. Analysis time ranges from few milliseconds to 291 milliseconds. It depends on the lesser on the program size, but more on the control flow because it takes time for the convergence. Now, effectiveness of GSOC, here is the speedups on different benchmarks. I can highlight the top 5 from the first 28 sets, and from the second 28 sets, I'm highlighting the top 5 performance. And if we see the performance improvement, the speed up is up to 1.9x and with 34% improvement with an average of 11%. One interesting insight is the optimization will yield the best performance if the host side computation time and the device side computation time are significant and comparable to each other. So they can actually perfectly overlap and hide each other's latency perfectly. In summary, we are introducing heterosync motion optimization, which moves the synchronization statements to improve the CPU-GPU overlap. We have introduced the GSOC, a novel compiler framework for optimizing the CPU-GPU synchronizations, and our comprehensive evaluation shows that our framework achieved up to 1.9x speedup with an average of 11%. You can see the artifact. Our artifact has won the Distinguished Artifact Award in ECU. So please play with it and give us like ample amount of feedback so we can like we have to do many more things on that artifact and we can improve that so much. Thank you.
Thank you, Robin, for the scientific analysis. We also like looking at the model.
Have you also evaluated looking to changing synchronous mem copies to asynchronous mem copies and streams?
Yes, wonderful question actually, because uh, my second project actually gives that we change the mem copies to the asynchronous mem copies, and as well as we also assign streams automatically to the CUDA mem copy asyncs as well as the kernels also, so they can overlap with the CPU computations, and the mem copies also can overlap with the kernel computations as well. So that is not our future work, it's already in submission actually. So hopefully we can see that soon.
Yeah, right. You are trying to do interprocedural dependence and all that, which is a, well-known tough problem. So out of the cases that you identified, which had opportunities, how many were you not able to prove dependence or independence rather?
Okay. So here is the thing that uh, the dependency analysis have two things. That's one is the data dependency and is the control flow dependency, as I have told. For the data dependency is the main bottleneck where we have missed the opportunities because of the alias analysis. So we have tried to use LLVM's basic AA first, which is not good at all. So we had to write our own interprocedural alias analysis actually from scratch, which we know that works for these kind of programs. Uh, but yeah, maybe that answers your questions. That
So you wrote your own.
yes.
Follow up the fact that because you have taken the PCI-based memory, have you tried on something like a grasshopper with unified memory?
We again, it's excellent question actually. We have coming up optimizations for the unified memory also. We are like that is our future work. We are working on that, the unified memory based optimizations. Yeah, but the one thing that we are not, when we don't have the access to the grasshopper, but we have the unified memory for the Ampere architectures. So we are testing on that, and it is actually a positive result that we are getting.
Well, let's thank the speaker again. Can get my good for. That's the question. That's why we are customizing the for the engine. So, this is the short one.
Yeah. Yeah. So hello everyone. Today I'm going to talk a bit about our plugin framework in ELD and also share some plugin examples that we have built using this framework. So we all know that linkers are a very underrated tool in the compiler toolchain. Uh, they play a very key role. They take all the input object files and they combine all those object files into a final binary. Now there are many available open source linkers today, from the classic GNU linker, Gold, LLVM's LLD, MCA linker, and the new kid on the block, uh, Mold. So as for a plugin framework, the main purpose is that it allows the users to customize the linker's behavior without making any changes to the core functionality of the linker. So you don't modify the core. You you generate plugins separately. Uh, these plugins are loaded as shared libraries along with the linker. So you can see P1 and P2 here are plugins and they are loaded as shared libraries. Yeah. Uh, so plugins can actually inspect and modify like all the key linker features and all the key linker components. So if you consider components like input sections, input files, and symbols, and also some key linker features like rule matching, LTO, garbage collection, plugins can modify all these functionalities, and also can you can inspect all these functionalities using plugins. The plugin framework does this by implementing some hooks that are called at key points in the linker pipeline. So for example, you can see a hook here and it's implemented between two key linker states in the pipeline, reading input files and linker script rule matching. So a hook is called before linker script rule matching, and these hooks are implemented by the plugins. Now these hooks are actually virtual functions that are implemented in a plugin base class, and these virtual functions can easily be overridden by the plugins, and they are called in the link pipeline here. So we have two different main types of hooks in the plugin framework. So one of them is the visit component hooks, and the other is the act before link state hooks. So the visit component hooks usually deal with the main components of the linker. So for example, sections, symbols, input files, and the other is the act before link state hooks. These are usually called before the any key link state in the linker. So for example, you can see the link states here, read input files, in initializing the linker, reading the input files, the linker performing rule matching, section merging. The second type of hooks that are act before the link state hooks, they are called before these key link states, and they can modify the link states that they are called before. So you can see the examples here. These are the hooks that we have implemented in ELD. Act before rule matching is being called before rule matching. Act before section merging is being called before section merging. Performing layout is called before performing layout, and so on. And also the other kind of hooks that I talked about, the hooks that deal with the key components of the linker. So the visit section hook, which is called after every input section that is being created. So if we take the input, read the input object file,
we create the input section, and then that we directly call the visit section hook. Now this hook is a virtual function, so it's by default a empty function like a skeleton. It doesn't do anything unless the plugin implements that hook by overriding. So we call that hook on this input section that has been just been created, and we do whatever logic we implement, whatever logic the plugin has defined. And after that, the cycle continues till we iterate through all the input sections. And also visit symbols are similar. We create input symbols and then we call this hook visit symbol, and then we implement the logic of the plugin if the plugin has implemented any logic for this hook by overriding. And then the linker continues with its normal task like resolving symbols, and then the cycle continues. We get a new symbol and so on. So now that we have a very high level overview of how the plugin framework works in our linker, I'm going to share some plugin examples that we have, some simple plugin examples that show the flexibility of our plugin framework and the plugins that are implemented with it. So before moving on to the examples, there are a few key concepts that would be necessary for the coming examples. So one of them is weak symbols. So, but before that, what is a symbol? Symbols are just functions or variables that you define in your program, and weak symbols are specifically functions or variables that can be overridden by other strong symbol definitions. So my symbol definitions, what I mean is you can see the three files here: 1.c, 2.c, and 3.c. All these functions, all these files implement the foo function. So 1.c has the default definition that we are used to seeing, int foo return 12. It's just a default definition that we implement. 2.c is just a declaration of the function with extern. So it expects to find the definition, the compiler expects to find the definition in some other file. And the third file 3.c has a weak attribute attached to the function. So this is basically a weak symbol. So whenever compiler encounters this situation, it directly uh, skips the weak symbol attribute definition, and the strong symbol overrides the definition, and foo will get the value of foo will get this definition from the strong symbol. Also, as for common symbols, they are uninitialized global variables that are not marked extern in the program. So you can see in 1.c there is int x. It's an uninitialized global variable. 2.c has a int x similarly. 3.c expects the definition of int x to come from somewhere, but since both the variables are uninitialized, it will get a common symbol error. Uh, so yeah, so the main example for the concepts, symbol checking. So we can common symbols, although they are necessary in our projects, they can lead to bugs sometimes. But the main question is how do we modify the core linker so that we can emit some diagnostic whenever we encounter weak or a common symbol. Now for that, of course, we would go to symbol resolution because that's the link state that deals with symbols. Uh, but it is not very practical to go on modifying the core linker for such cases. So we might want to emit some diagnostic or some other thing, and we can't keep on modifying the core linker for it because the code would become bloated, and it's not a very scalable solution to modify the core linker for this. So the answer is linker plugins. Oh, so yeah, this is just symbol resolution. How what symbol resolution does, it is basically resolving the definition of any symbol that has been defined or that has been declared. So you have three files over here. One defines the variable foo, one has a weak attribute attached, and one is a common symbol. So strong symbol will take priority here and it will consider the strong definition. Symbol resolution will do the job and foo will finally get a value of 3. Uh, so where will we call this linker? Where will we call the hook for creating the linker plugin? So since we are dealing with a core component of the linker, as I told you, there is act on components, visit components hook in the link plugin framework. Uh, so you can see over here, this is the hook as it exists in the linker. It's a virtual function. and it is empty. It's just a skeleton function because no plugin has defined that function. So whenever by default this function hook is called in the link state pipeline, it doesn't do anything and the linker continues in its merry way doing its job. But now since we want to emit diagnostics for weak and common symbols, the plugin will implement this hook. So it will be something like this. So this is visit symbol. It is taking the input symbol as input. Uh, and it is checking if the symbol is common or weak. And if it's common or weak, we will emit an error diagnostic over here. And since we are emitting an error diagnostic, the link will end and we will error out. But we could also emit warning diagnostics if the user just wants a warning if we encounter weak or common symbol. But usually you don't run this check on all the files in your code. There might be some shared libraries in your project or some other files which you have not implemented. So we could easily implement some check for that. So should check common symbols for the input file. We get the input file from the symbol only. This is an API. So get input file from the input symbol. We get that input file and we implement some check to check if the input file is a program file which we have implemented. So we'll only check those files and we'll get that condition over here. We'll add that condition in the hook. So we will basically only implement this logic on those files. So now that we are done with one example, the next example is about layout optimization. But the question is, what is image layout? So image layout is a high level overview of image layout is that the linker defines this, so which tells the user the linker defines where each byte of memory from your code will be placed in the final image through the image layout. And why is it necessary? So cache locality depends on where the frequently executed functions are placed. Uh, we could place the frequently executed functions in fast and slow, fast memory. Uh, there are some hardware specific constraints in some embedded devices. And also the main thing is a good layout can help reduce our memory footprint, which is very critical in embedded projects. So here we have a file where we have changed the input section names for all these functions through a macro. So the input section names would be something like text.hot.1. You can see the macro over here. So we have changed it for everything, and these priorities that we are putting the numbers over here, they they show how frequently are the functions executed. We have the linker script over here besides this, which has the sections command and this input pattern. So all these functions that you can see over here with input section names like this will be placed in the output section A. But now the main problem is the order won't be in the ascending order like 1, then 2, then 14. It will be in the order in which the functions are defined. So how do we change this? But before this, of course, plugins can do this. But where do we call the hook for the plugins? Since we are dealing with the layout stage of the linker, we'll call the act before performing layout hook for this. And you can see it's just a skeleton by default until the plugin implements some logic in for this function by overriding it. So before performing layout, there's a section merging stage where all the input sections that we get from the program file are that match some rule in the linker script are merged into one intermediate section for each rule. So output sections are formed from these intermediate sections only. So if we can modify these intermediate sections somehow, we can get the proper order for for the functions that we had defined before. So how can we do this? By using some linker wrapper APIs, add chunk, remove chunk, and update chunk. So they'll take this intermediate section with these input sections which are which are in the order in which the functions were defined. We'll remove chunks like we'll remove 14 and we'll remove 2, and then we'll add the chunks again according to the priority order. So 2 will come before 14 and so on. Further improvements could be through section budgeting. What if all these functions that we have defined here don't fit in the output section A, which has a max size of 200 bytes? What if it's exceeding? Again, we could modify the linker core logic, but as we had discussed, it's not a very scalable solution. So what we can do in this case is that plugins have support for reading config files that we pass through the plugin framework. So here in the config file, you can define that the max size of the output section is like A is 200 bytes, and if there's an overflow, if there are some sections that don't fit in output section A, they will go in over in the second in the B output section, and like plugin can read this map file and it can do the read, like it can remove the chunks as the APIs we had discussed, remove chunk, add chunk. It can remove the chunks from A, it can remove the chunks from A, and it can put those output chunks in B so that the overflow case is resolved. And apart from that, it doesn't make sense to modify the input section names in the during the compilation time only, because we won't know which function is executed how many times to decide which function is hotter or not. And also it pollutes the input section names, and it could lead to some debug issues. So what we can do is we can run the link step once, we can get the final binary, and we can do some PGO analysis on that binary and get to know which function is executed how many times, and then we can uh, pass a config file as before to the plugin, and it will read this config file and it will automatically instruct the rule matching stage of the linker to map these original input section names to the modified input section names, which have the priority of each function attached. So 114 for each of the functions. So yeah, so that's it. Thank you.
Thanks, Rishabh. It was quite an interesting talk. Do you have a question?
So regarding the plugin mechanisms which you mentioned,
Mm.
visit pattern or add
Yeah.
pattern, are there any other patterns which are supported?
No. So currently we have these two patterns, and we cover like majority of the linker in this.
Because, so for example, taking your example of principles, right?
Yeah.
How would you handle a case where, let's say, you want to emit diagnostic only if there are inconsistent weak definitions? Like, I have one weak definition which is 5, which is initializing variable with 5.
Okay.
And another weak definition which is initializing with 7. And
Okay.
we want to emit diagnostic only if there are inconsistent weak definitions, because the visit pattern cannot handle that kind of thing.
Okay. So yeah, maybe I need to check. We maybe can't. Yeah, we can't handle that case with visit symbols. So yeah, there are some cases.
Any more questions? You also support NVO with these plugin infrastructure.
Yes, we do. We have some plugins downstream, so we have not open sourced them, but yeah, we support it.
Okay.
Yeah.
I have a quick question as well. So, how many, in general, for real programs, how many weak and common plugins do you have? How many times do you have to emit the diagnostics?
So the main thing is the plugins are not only for diagnostics or something. It is also for, suppose you want to cache something before some link step. So for example, rule matching, you could easily cache that. So for that, we can create a plugin, and it can speed up the rule matching significantly and increase developer productivity. So yeah, so there are many such cases. It's not only for diagnostics. It's like you can do anything what you can do in a linker in a plugin.
Alright, let's thank Rishabh once more. So the session ends here. We have few set of announcements before we end. Yeah.
The volunteers for announcements, I just think that we should give a big round of applause to
Well, from this side.
session chairs.
From one of them.
Almost at on time performance. We are almost on time as we promised, and our type of this has been very critical to us. Tomorrow also we will have something similar, and we look forward to seeing all of you. We have poster sessions, we have presentations from Hackathon. So I'll then hand it over to the volunteers to make any other announcements for the day.
So yes, you can disperse, and I just request the members of the program committee and the speakers to come forward. We can take a picture before we are leaving.
Keep this Hey, ಇದು ಸ್ಟಾಪ್ ಮಾಡೋದಾ ಸ್ಟ್ರೀಮಿಂಗು? ಸ್ಟ್ರೀಮಿಂಗ್ ಸ್ಟಾಪ್ ಮಾಡಿ ಸ್ಟಾಪ್ ಮಾಡ್ಬಿಟ್ಟು ಏನ್ ಮಾಡಿ